The James Webb Space Telescope was built to confirm our cosmic origin story, but instead, it just broke the universe. From impossible galaxies older than the universe itself to a failing standard model of cosmology, scientists are facing a reality-shattering crisis that could rewrite physics as we know it. Peering into the remote cosmos, the James Webb Space Telescope discovered that two-thirds of distant spiral galaxies rotate in the exact same direction. This alignment completely violates established cosmological principles. Prepare to explore galaxies older than the universe, mysterious crimson specks concealing colossal beasts, and a mind-bending hypothesis suggesting our universe exists within a giant black hole. When the initial photographs downloaded, the research team in Baltimore was completely blindsided. The observatory had only reached its orbital destination a few months prior, and technicians were actively adjusting the optical components. Despite this, the premiere deep space snapshot delivered an astonishing surprise. The frame was packed with hundreds of incredibly crisp, luminous galaxies. These ancient structures displayed an impossible level of clarity, occupying regions of space that traditional textbooks declared entirely empty. This observatory is an absolute giant of engineering. Positioned roughly 1 million miles from Earth, 4 times the lunar distance, it boasts a golden reflector spanning nearly 21 feet, matching a tennis court double's lane width. Its primary function is capturing infrared radiation, originating from before our planet or sun existed. By the time these light waves strike the golden surface, they have journeyed through the void for over 13 billion years, effectively turning the device into the ultimate chronological viewing machine. Researchers aim the optics at a minuscule sliver of the heavens, an area so tiny that a single grain of sand held at arm's length would obscure it. They anticipated spotting a handful of blurry blobs or primitive stellar clusters. Instead, they uncovered brilliantly illuminated, fully developed galactic metropolises. These massive stellar cities were located at extreme distances, dating back merely a few hundred million years post-Big Bang. This revelation created the first fracture in our understanding. According to conventional models, the infant universe should have been a tranquil, sluggish environment where raw materials were still condensing to ignite the first stars. Those primordial formations were predicted to be diminutive, dim, and widely dispersed. However, a single afternoon of observation shattered that paradigm. Staring intently at his monitor, a veteran stargazer whispered a profound observation. He noted that the formations appeared excessively ancient, remarkably structured, and impossibly massive. His assessment was entirely accurate. Within weeks, a flood of academic publications emerged, quickly followed by intense scientific debates. Certain primordial systems appeared to possess the mass of 10 billion suns, while others seemed to dwarf our Milky Way. Consider that our home galaxy required approximately 13 billion years to achieve its present spiral structure. Yet, these remote anomalies allegedly accomplished the exact same feat in just 500 million years. The situation is comparable to flipping through a family album, spotting a photograph of a newborn infant, and realizing the baby is already dressed in a tailored business suit while holding a briefcase. Experts refer to this epoch as the cosmic dawn. Theoretical models dictated that initial stars would ignite gradually, eventually clustering together to form modest galaxies and larger cosmic webs. The new data, however, revealed a much more rapid, compact, and mathematically defiant reality. Initially, cautious scientists attempted to rationalize the anomaly. They suggested distance calculations might be flawed, interstellar dust could be creating optical illusions, or mass calculations were simply exaggerated. These were logical hypotheses. Nevertheless, every subsequent batch of photographs exacerbated the dilemma. The influx of data continuously revealed heavier, brighter ancient structures in regions that conventional physics guaranteed would be barren. Every fresh snapshot dragged researchers further from their accepted narrative, forcing mathematical models into uncharted realms they were never designed to navigate. Soon after, an investigator detected an even more baffling phenomenon. This mystery had nothing to do with the apparent age or staggering weight of the formations, but rather their rotational dynamics. This breakthrough originated from a fundamental inquiry regarding the maximum allowable mass of a galactic system during the universe's infancy. Traditional frameworks insist the answer is incredibly tiny. Cosmic structures are theorized to expand similarly to a snowball tumbling down a slope, gradually accumulating material over eons. Consequently, the earliest examples ought to be delicate, hazy, and structurally fragile. This was precisely what experts anticipated when targeting the furthest observable regions. Instead, they uncovered a select collection of stellar islands that flagrantly violated every established rule. Mike Boland Culkin, an astronomy associate professor at the University of Texas at Austin, closely examined 6 specific examples. While half a dozen might seem like a modest sample size, it proved sufficient to rattle the bedrock of modern astrophysics. These targets were situated at distances reflecting an era merely 500 to 700 million years post-creation. During that epoch, the cosmos was essentially an awkward adolescent, still defining its ultimate structure. Astonishingly, every single one of those 6 systems boasted a mass exceeding 10 billion times that of our Sun, with a few appearing to outsize the Milky Way. Keep in mind, our home galaxy required 13 billion years to reach its current grandeur, whereas these remote relatives achieved a comparable scale in a fraction of that duration. Culkin quietly remarked that accurate mass readings would plunge the field into uncharted territory. Hearing those specific 3 words from such a meticulous researcher is the academic equivalent of launching an emergency flare into a pitch-black sky. The statistics were so bizarre that numerous experts initially rejected the findings outright. They hypothesized that redshift calculations could be inaccurate, stray light might be contaminating the frames, or cosmic dust was obscuring reality. Consequently, rigorous verification campaigns commenced, utilizing additional observatories and advanced spectroscopic techniques to separate light into distinct color spectrums and reveal chemical signatures. While a few initial targets proved to be false alarms upon deeper inspection, many others remained valid, and countless fresh examples continuously emerged. The count ballooned from 6 to dozens, then hundreds. Researchers from the University of Missouri directed infrared sensors toward the deep sky, identifying approximately 300 entities that shone far too intensely for their presumed chronological age. Picture strolling into a hospital maternity ward only to discover the majority of infants are already walking around and demanding car keys. That analogy perfectly captures the sheer magnitude of this astronomical shock. The prevailing cosmological paradigm, frequently referred to as the lambda cold dark matter model, dictates a highly gradual construction process. Minuscule fluctuations in the primordial void supposedly drew raw materials together, allowing tiny formations to combine into progressively grander systems over unfathomable timescales. However, the latest visual evidence depicts a phenomenon that completely skips those incremental steps, effectively reaching the penthouse before the building's elevator is even constructed. Desperate to salvage prevailing theories, astrophysicists suggested every conceivable workaround. They theorized that stellar ignition might have occurred much more rapidly, the earliest stars could have been exceptionally gigantic, or an entirely unknown illumination source was skewing the data. Unfortunately, every proposed solution merely patched one hole while tearing open another. As investigators probed deeper, the underlying truth became undeniable. The infant cosmos, revealed by the telescope, simply refused to align with the theoretical universe constructed by physicists. That was strange enough on its own. But the very next revelation didn't just tweak the cosmic clock, it completely upended our understanding of how matter actually moves through the void. To truly grasp the panic induced by a specific set of 6 ancient galaxies, we need to mentally travel back to the universe's infancy. Imagine the cosmos a mere 500 million years post-Big Bang. It was an incredibly hot environment, actively birthing its very first stellar generations, essentially still under heavy construction. During this epoch, the cosmic ingredient list was incredibly basic, dominated almost entirely by helium and hydrogen. The heavier elements required to construct things like planets, human bones, or even your morning coffee mug simply hadn't been forged in significant quantities yet. Consequently, astronomers expected the galaxies of this era to resemble tiny, disorganized gas clouds and loose stellar clusters, essentially the cosmic equivalent of a half-finished housing development. Instead, the James Webb Space Telescope revealed a skyline of fully constructed metropolises. A research group from Australia's Swinburne University of Technology was the first to pinpoint these 6 colossal structures. They discovered that each object crammed an astonishing amount of stellar mass into incredibly tight spaces. We are talking about an estimated 10 billion times the mass of our Sun for each one, with a single candidate potentially eclipsing the sheer scale of our own Milky Way. To visualize this sheer magnitude, imagine a solitary galaxy containing a greater number of stars than all the neighboring galaxies in our local cosmic vicinity put together. However, the true mystery wasn't just their immense weight, it was the blistering speed at which they accumulated it. Subsequent evaluations pointed to a scenario that bordered on the impossible. For these structures to achieve such colossal masses so quickly, they would have had to transform practically all of their accessible gas directly into stars. We are talking about a conversion efficiency approaching 100%. Compare that to modern galaxies, our own included, where the efficiency hovers around a mere 5 to 10%. Today, the vast majority of gas simply drifts through space, pushed by stellar winds or tugged by gravity, without ever igniting into a star. Think of it like a bakery that miraculously converts every single grain of flour, every drop of water, and every tiny speck of sugar into flawless loaves of bread with absolutely zero waste. Now imagine that exact same bakery operating at 10 times its normal speed. That is the staggering level of stellar manufacturing these ancient objects demanded. Naturally, some experts attempted to dial back the rising panic. They proposed that these mass calculations might simply be inflated. Extremely luminous galaxies can be notoriously deceptive. If the bulk of the emitted light originates from a small handful of unusually gigantic stars, the overall mass calculation could easily be skewed upward. Other investigators hypothesized the presence of a hidden component. Maybe these weren't purely stellar galaxies at all. Perhaps an incredibly bright, hidden engine was lurking at their cores, pumping out extra radiation that artificially inflated their apparent weight. As it turns out, this hidden engine concept provides a crucial clue we will explore later, a hint pointing toward black holes, but not the standard variety. These would be exotic seeds planted long before the first star ever ignited. For the moment, however, these 6 anomalous galaxies served as a massive red flag. They signaled that the infant universe was either vastly more efficient at building things than we ever imagined, or it was playing by a completely unknown set of physical rules. Both scenarios came with a hefty price tag. Accepting the first meant completely overhauling our models of star formation. Embracing the second meant tearing down the foundational framework of cosmic evolution, altering the very starting conditions of the universe. Attempting to calm the waters, a Johns Hopkins University research team headed by Nashwin Sabti challenged the most extreme conclusions. They demonstrated that tweaking the standard cosmological model to accommodate these behemoths ended up breaking other well-established predictions that perfectly matched older Hubble data. Their final verdict was measured and cautious. The flaw might not be in our overarching cosmology, but rather in our grasp of how galaxies and stars behave under extreme, early universe conditions. The scientific community remains locked in this debate, with some fiercely defending the current paradigm while others watch the cracks widen. Yet, while the astronomical community was fiercely debating redshifts and stellar masses, a much subtler revelation was hiding in plain sight within the exact same Webb dataset. This new pattern had nothing to do with luminosity or physical size. It was all about movement. We have known for roughly 100 years that galaxies rotate. Spiral galaxies, which resemble brilliant cosmic pinwheels, feature sweeping arms that wrap around a luminous central core. Depending on your viewing angle, the coiling of the arms, and the tilt of the galactic disk, these structures will appear to spin either clockwise or counterclockwise. If the universe is truly random, you would logically expect an even distribution. It should be a perfect 50-50 split, much like flipping a coin millions of times and watching the results naturally balance out. But that is absolutely not what the James Webb Space Telescope revealed. Lior Shamir, a computer scientist and associate professor at Kansas State University, decided to put this assumption to the test. He extracted his data from the JWST Advanced Deep Extragalactic Survey, conveniently abbreviated as JADES. This specific survey operates as a deep field observation, meaning it locks its gaze onto a single, tiny patch of the sky for extended durations to capture the incredibly faint light of distant objects. Thanks to Webb's unparalleled sensitivity, the resulting imagery is vastly sharper than anything Hubble could achieve at those specific wavelengths. Shamir utilized a strictly quantitative approach to analyze the spiral galaxies within this field. He carefully measured the curvature of their arms, the tilt of their disks, and the specific rotational direction for every galaxy clear enough to study. Ultimately, 263 galaxies met his strict criteria, each one representing a tiny, glowing pinwheel from the dawn of time. The findings were absolutely astonishing. Approximately two-thirds of these galaxies were spinning clockwise from our earthly perspective, while only about one-third rotated counterclockwise. This is far from a random coin toss. This is the equivalent of flipping a coin hundreds of times and watching it land on the exact same side 2 out of every 3 times. From a statistical standpoint, the probability of this occurring in a genuinely random universe is incredibly minuscule. Shamir specifically highlighted just how visually apparent this imbalance truly is. Even though his team relied on rigorous quantitative software, the discrepancy is so glaring that an untrained observer could easily spot it. You don't need advanced mathematical tools, you just need your eyes and a pointing finger. Naturally, the immediate instinct is to assume a systemic error. Perhaps the survey only covered a biased, localized patch of the sky. Maybe the specific orientation of the observational field naturally favored one rotational direction. Or perhaps the algorithms and human classifiers possessed an inherent bias. Every single one of these potential flaws had to be rigorously investigated and ultimately dismissed. The JADES field is strategically positioned near the galactic pole, looking perpendicular to the Milky Way's own disk. This is highly advantageous because it provides an unobstructed, dust-free view out into the deep cosmos. Furthermore, the rotational asymmetry remained robust across various measurement techniques. It even echoed findings from older Hubble ultra-deep field observations, albeit with much smaller sample sizes. Webb simply validated this trend using a vastly superior and more expansive dataset. These groundbreaking findings were officially published in the monthly notices of the Royal Astronomical Society in March of 2025. While the paper's title was straightforward, its underlying implications were earth-shattering. We are faced with a stark choice. Either early galaxies genuinely possess a directional preference, or our entire methodology for calculating deep space motion and distance is fundamentally flawed. Both alternatives are incredibly disruptive. The first forces a rewrite of cosmology, while the second invalidates half a century of distance measurements. Let's return to that crucial two-thirds ratio. Out of the 263 analyzable galaxies, roughly 175 spun clockwise relative to us, while about 88 spun the opposite way. This is a massive, undeniable gap. In the realm of statistics, such a glaring imbalance indicates the presence of a preferred axis. It sounds like a benign technical term, but its actual meaning is profound. A preferred axis implies that the universe possesses a specific directionality. It isn't just a chaotic jumble of random motions or an evenly distributed spread of spin. Instead, there is a fundamental tilt woven directly into the very fabric of space, established during the universe's earliest moments and preserved through 13 billion years of galactic evolution. This concept directly violates one of the most sacred principles in modern physics: isotropy. Isotropy is the assumption that the cosmos looks identical in every single direction, meaning no specific angle or location holds a special status. When you pair isotropy with homogeneity, the concept that matter is distributed evenly on a grand scale, you get the absolute bedrock of the standard cosmological model. Everything from the mathematics of general relativity and the predictions of the Big Bang to the structure of the cosmic microwave background relies entirely on this principle. Web-spinning galaxies are actively drilling a hole through this foundational pillar. If the cosmos truly favors one rotational direction, it means the universe retains a memory of an initial condition established long before galaxies even existed. Skeptics quickly pointed out the most obvious counterargument: the universe is unfathomably vast, and Webb only examined a microscopic window. Could this asymmetry just be a localized quirk of that specific sky region? It is certainly possible. However, Shamir countered by pointing out that older Hubble data from entirely different sky sectors showed similar, albeit fainter, trends. Whenever a sufficiently powerful telescope peers at distant galaxies, this pattern keeps surfacing. Furthermore, the universe already harbors other bizarre anomalies hinting at directional bias. The cosmic microwave background, the ancient afterglow of the Big Bang, features strange alignments of temperature fluctuations that scientists have dramatically dubbed the axis of evil. Additionally, massive clusters of galaxies appear to be drifting in specific directions, a phenomenon known as dark flow. While each of these individual anomalies is highly debated and easily dismissed on its own, stacking them together reveals a compelling pattern. Among all these mysteries, the spinning galaxy data is by far the most straightforward. You don't need a PhD in mathematics to understand it. You can literally see it in the photographs. If this asymmetry holds up, the consequences extend far beyond the realm of astronomy. It would prove that the universe carries a distinct fingerprint, a sort of cosmic handedness originating from pre-galactic times. Physicists would then be forced to explain the origin of this handedness. One potential explanation is incredibly mundane. The Doppler effect, generated by our own Milky Way's movement through space, might be artificially brightening galaxies that spin opposite to us, making them appear more frequently in our surveys. If this is the case, Webb isn't detecting a universal asymmetry at all. It is merely capturing a reflection of our own local motion. The alternative explanation, however, is anything but boring. It suggests that the universe itself was born spinning. And if the cosmos was spinning at birth, whatever preceded it must have been spinning as well. Initially, the concept of a spinning universe sounds completely absurd. The universe encompasses everything, so there is no outside to spin relative to and no before to spin from. What would it even spin around? Surprisingly, the mathematics actually permits it. General relativity, the framework Albert Einstein finalized over a century ago, is perfectly capable of describing a rotating cosmos. Back in the 1940s, mathematician Kurt Gödel proved that Einstein's equations contain valid solutions, where the entire universe slowly rotates around a central global axis. Historically, physicists have brushed off these solutions as mere mathematical novelties rather than physical realities. But mathematical equations do not care about human preferences. They simply allow what they allow. A rotating universe would exhibit incredibly bizarre physics. Light traveling near the axis of rotation would bend in highly unnatural ways. In extreme scenarios, the flow of time could actually fold back on itself, creating closed loops that theoretically allow paths into the past. Gödel found this implication so deeply unsettling that he argued the equations required additional constraints. As decades passed, the concept of a spinning cosmos was pushed to the fringes. The Big Bang model, with its perfectly uniform expansion, became the undisputed star of the show, and cosmic spin was relegated to a minor footnote. Then the James Webb Space Telescope launched, and these spinning galaxies suddenly demanded our attention. If a preferred cosmic axis truly exists, the most elegant explanation is that the universe has been rotating since its inception. This primordial rotation would have stamped a directional bias onto the earliest matter. As galaxies condensed from this material, they would naturally inherit that preferred spin. It wouldn't be a perfect alignment, because chaos and local gravity would disrupt the pattern, but it would create a statistical lean, perfectly matching the 2/3 clockwise and 1/3 counterclockwise ratio we observe today. The discrepancy is subtle enough to require careful measurement, yet massive enough to be undeniably real. This is precisely where the controversy explodes. A rotating universe absolutely requires an external frame of reference to measure that rotation against. In standard physics, this is a massive hurdle, because the universe is defined as the totality of all space and time. There is no external observer floating in the void with a stopwatch and a compass. Many physicists use this exact logical roadblock to dismiss the idea entirely, but others view it as a profound clue. They argue that a rotating universe makes perfect logical sense if our cosmos is not the only one in existence. It implies our universe might be contained within a much larger structure, like a single bubble in a vast cosmic foam, or one room inside a colossal, multi-dimensional house. The second possibility is even more mind-bending. If our universe is rotating relative to a larger external framework, and if that rotation originated from a specific source, that source could be the most extreme object in all of nature, a black hole. Specifically, a supermassive black hole residing in a larger, parent universe, where collapsing matter falling inward spawned a brand new region of spacetime that we now call our cosmos. While that concept sounds like pure science fiction, it is actually a legitimate theoretical proposal championed by highly respected physicists. Building directly on that mind-bending premise, the plot only gets thicker. If a black hole actually gave birth to our cosmos, the implications would fundamentally rewrite everything we know. It would explain the relentless march of time, the ongoing stretching of space, the specific visual patterns in the cosmic microwave background, and even our capacity to ponder these mysteries. For 13 billion years, ancient light has carried secrets from the dawn of creation. The James Webb Space Telescope is finally the first tool sensitive enough to decipher this script. Surprisingly, the message it decodes points to an origin story completely unlike anything we anticipated. Scientists refer to this framework as black hole cosmology or occasionally Schwarzschild cosmology. That second name honors Karl Schwarzschild, the German physicist who first cracked Einstein's equations regarding black hole environments back in 1916. The core concept is straightforward to explain, yet mind-boggling to grasp. Essentially, everything we observe is nestled within a black hole residing in a grander parent universe. Picture a standard black hole externally. It appears as a pitch-black orb bordered by a strict point of no return called the event horizon. Once you pass that threshold, escape is impossible. Internally, however, the geometry behaves bizarrely. Space and time literally exchange functions. The central singularity ceases to be a physical location. Instead, it becomes an inevitable future moment, as inescapable as tomorrow. Within this model, infalling material avoids being squashed into an infinitely dense dot. Rather, it undergoes massive expansion. Instead of collapsing, the plunging matter rebounds into a freshly created spatial domain stretching outward along its own unique timeline. To an observer inside this newborn realm, that initial bounce perfectly mimics the Big Bang. The subsequent stretching mirrors cosmic inflation, while the original event horizon acts as the edge of their observable sky. Should our reality have originated this way, multiple cosmic puzzles click into place. The notorious flatness of space becomes a natural byproduct, because material tumbling into a black hole arrives smoothly, making the resulting expansion perfectly even. Furthermore, the forward march of time gets a physical explanation. Since stuff crossing the parent event horizon is forced inward, this unidirectional flow establishes a permanent cosmic compass. The new universe adopts this temporal flow, meaning the past sits nearer the outer boundary while the future pushes deeper inside. Additionally, any spin possessed by the parent black hole would stamp a distinct rotational axis onto the newborn universe, an axis Webb's observations seemingly recall. Nikodem Poplawski, a theoretical physicist at the University of New Haven, has advocated for this framework for years. Speaking to journalists about the Webb discoveries, he noted that a rotating parent black hole offers the simplest explanation for our universe's rotation, expressing immense enthusiasm regarding potential validation. Nevertheless, the broader cosmological community remains unconvinced. While mathematically beautiful, the concept lacks a robust suite of testable forecasts. It also introduces a dizzying philosophical dilemma by nesting our reality inside a larger one, prompting inquiries about what contains that parent reality. Certain iterations embrace an endless fractal chain, where black holes birth universes that grow their own black holes, creating an infinite cosmic tree. Alternative models propose a self-sustaining loop. Visualizing this is difficult, but that is by design. The conventional Big Bang is equally tough to imagine. An infinitely dense speck erupting into everything is hardly intuitive. We embrace the standard model simply because its mathematics align with empirical evidence. Black hole cosmology demands the exact same leap of faith, different equations, but the identical requirement to produce verifiable predictions. For years, testing this seemed impossible. That changed when Webb focused on the JWST field, tallied the rotational directions of distant galaxies, and provided the exact breakthrough the theory needed. A distinct rotational pattern suggesting our cosmos retains the memory of its creator. Poplawski's specific take introduces extra complexity. His research utilizes Einstein-Cartan theory, a modification of standard general relativity. While conventional relativity views spacetime as smoothly curving, Einstein-Cartan incorporates torsion, describing how spacetime twists around spinning matter. Under everyday circumstances, this effect is minuscule. However, within the ultra-dense environment of a black hole, this twisting force becomes dominant. Poplawski's models demonstrate that torsion halts gravitational collapse just before a singularity forms. Rather than ending in an infinitely dense point, the matter experiences a massive bounce, tearing open a brand new spatial domain. This freshly minted region operates as a baby universe, transforming black holes into literal cosmic doorways. This infant cosmos absorbs key traits from its progenitor, including mass, spin, and temporal direction. Inhabitants would witness a rapidly expanding, hot environment, dubbing it their Big Bang. They would eventually construct telescopes and debate their origins, oblivious that their entire existence is contained within a dark orb floating in an older sky. Detailing this in his publications, Poplawski highlighted a nuance regarding time. Because matter only plunges inward past an event horizon, this one-way traffic transfers its asymmetry to the newborn universe via torsion, granting the new reality a permanent, inherited arrow of time. Bringing this back to Webb, the implications are staggering. If a spinning black hole birthed our reality, that original rotational axis would be permanently imprinted on our cosmos. Consequently, galaxies condensing within our universe would exhibit a slight, statistical preference for spinning in one direction, perhaps a 2/3 to 1/3 ratio, aligning perfectly with the imbalance discovered by Lior Shamir. When questioned about these JWST observations, Poplawski was candid. He stated that confirming a preferred galactic spin axis would strongly bolster the concept of black holes birthing new realities, adding that verified results would thrill him. Notice the cautious phrasing. He wasn't declaring triumph. He was simply highlighting his framework's forecast, presenting the hypothesis, the new data, and the correlation. Naturally, plenty of scientists remain doubtful. Critics suggest this bias might stem from observational selection effects, Doppler shifts, or the Milky Way's movement. Every alternative must be debunked before the baby universe concept gains acceptance. Truthfully, the current data is merely intriguing, relying on a single study and a few hundred galaxies. Proving our black hole origins requires vastly more observations across diverse regions. Fortunately, that undertaking is underway. Independent groups are hunting for matching asymmetries, while upcoming surveys aim to analyze the spin directions of millions of galaxies. The coming decade will determine if this doorway hypothesis holds water. Should it prove correct, every black hole captured in a Webb photograph transforms from a gravitational vacuum into a potential cosmic nursery, a silent gateway to an alien universe we can never reach. Yet, while researchers debated parent black holes and spinning universes, a different fracture split the standard model wide open. This issue had nothing to do with cosmic rotation. Instead, it struck at the foundation of astrophysics, the exact speed of our expanding universe. In 1929, Edwin Hubble delivered a monumental 20th-century breakthrough. He proved faraway galaxies are fleeing from us, with their retreat accelerating the further out they sit. The cosmos was no longer a frozen backdrop. It was actively stretching, proving space had a definitive starting point, a history, and a clear trajectory. Scientists dubbed this speed the Hubble constant, a vital metric revealing how rapidly space pulls apart. Pinning down this figure allows astrophysicists to determine the universe's age, track galactic drift, and forecast its ultimate fate. For decades, the scientific community hunted for this elusive value, building superior telescopes and refining techniques. By the early 2000s, the consensus rested at roughly 70 kilometers per second per megaparsec. Then a frustrating roadblock emerged. Two distinct observational techniques yielded conflicting results. The first approach relies on the cosmic microwave background, the faint radiation lingering from 380,000 years post-Big Bang. Feeding these ancient light measurements into the standard cosmological model and projecting them forward via Einstein's relativity yields a Hubble constant of approximately 67.4 kilometers per second per megaparsec. Conversely, the alternative technique focuses on Cepheid variables, a unique class of pulsating stars. These beacons rhythmically dim and brighten, and their cycle duration reveals their intrinsic luminosity. Contrasting their true brilliance with their apparent dimness allows astronomers to calculate exact distances. Climbing this distance ladder to gauge remote galaxies lets researchers compute recession speeds, delivering a Hubble constant closer to 73. Logically, these figures ought to align perfectly, but they stubbornly refuse. While a discrepancy under 10% seems trivial daily, it represents a massive chasm in cosmology. Such a mismatch implies our standard model lacks a crucial component, perhaps an unknown force, particle, or unrecorded early cosmic phase. Branded the Hubble tension, experts scrambled for over a decade to bridge the divide. They wondered if dense star clusters skewed Cepheid data, or if flawed dark matter assumptions tainted the cosmic microwave background readings. Leading the charge was Adam Rees, a Johns Hopkins University Nobel laureate and dark energy co-discoverer. He spearheaded a team pushing the Cepheid technique to unprecedented exactness. By 2019, Hubble Space Telescope observations shrunk the margin of error so drastically that the conflicting numbers could no longer be dismissed as statistical noise. Enter the James Webb Space Telescope. Boasting superior resolution, Webb's infrared vision effortlessly cut through the stellar crowding and cosmic dust that plagued Hubble. The stakes were high. If Cepheid calculations were flawed, Webb would expose the mistake. If they held up, the tension would be validated. Aiming at the exact same galaxies, Webb employed three distinct analytical techniques, including innovative approaches bypassing Cepheids entirely. After compiling an extensive dataset from its initial 2 years, the answer arrived in late 2024. The original figures held firm. The flaw definitely did not lie with Hubble's data. As Rees explained, the mismatch strongly indicates our fundamental comprehension of the cosmos remains incomplete. Webb eliminated the simplest excuses. The tension was genuine, proving the universe ignores our mathematical rulebook. A decade-long headache solidified into a permanent structural fracture. To appreciate the Hubble tension, imagine baking a cake. Think of the standard cosmological model as the recipe the universe followed for 13 billion years. Start with hydrogen, fold in dark matter, sprinkle dark energy, let it expand, and stir in gravity. The final product perfectly resembles today's cosmos. Assuming this recipe is flawless, checking the expansion rate at any point should yield the same measurement. Whether gauging the infant universe via the cosmic microwave background or checking the local universe using nearby supernovae, the numbers must agree. Yet, they clash. Our local neighborhood stretches roughly 9% faster than early universe data suggests. That gap is the tension. While 9% sounds trivial, picture a wristwatch dropping 1 second every 20 seconds. Let that error compound over years, and you end up in a completely different time zone. The cosmic equivalent operates similarly. Stretch a 9% miscalculation across 13 billion years, and suddenly you have galaxies in wrong locations, stellar ages defying logic, and a future trajectory wildly diverging from forecasts. Therefore, either the early data is flawed, the late data is flawed, or the underlying model is broken. Thanks to Webb, we can cross the first two off the list. So what is the missing ingredient? Certain theorists propose a fleeting surge of repulsive force during the cosmos's infancy. This early dark energy would have inflated space rapidly before vanishing. Tossing this into the mix adjusts the early expansion rate to harmonize with local observations. The catch: no one has ever detected it. Lacking an associated particle or distinct signal, it remains a mathematical placeholder. Other experts suggest known dark energy might not be static. Fresh data from the Dark Energy Spectroscopic Instrument implies dark energy might be weakening. If true, the universe's growth would eventually decelerate or collapse, rather than accelerating forever. Meanwhile, another camp advocates tweaking gravity itself, suspecting Einstein's equations require a large-scale adjustment. While modified gravity concepts have a long history, none have become the accepted standard. Finally, some suggest expansion speeds vary by region. We could sit inside a colossal void where expansion outpaces the universal average, making the tension a local illusion. Webb is actively testing these theories. By surveying distant galaxies, it charts the cosmic web across vast distances older instruments couldn't resolve. Every fresh data point either exacerbates the tension or drops a clue regarding a solution. Thus far, the mystery remains unsolved, and the fracture only grows wider. As Adam Rees and Johns Hopkins colleague Mark Kamienkowski note, cracking the Hubble tension might unlock secrets behind other anomalies. Cosmologists aren't just hunting one puzzle, they are watching a stack of mysteries accumulate. From impossibly mature early galaxies and strange rotational asymmetries to this stubborn expansion rate, these phenomena could be deeply interconnected, narrating the exact same cosmic story in completely different languages. Building directly on those interconnected cosmic mysteries, the James Webb Space Telescope introduced an entirely new puzzle to the mix, a bizarre population of minuscule, crimson, and universally glowing objects. But before we dive into those crimson specks, we have to revisit the stubborn Hubble tension. For a long time, the most comforting explanation for this expansion rate discrepancy was simply human or instrumental error. Scientists figured the underlying cosmological model was perfectly fine, and the universe was behaving exactly as expected. The blame fell squarely on the tools, particularly the local universe measurements relying on Cepheid variable stars. These Cepheids reside in the chaotic, dusty, and densely packed disks of relatively young galaxies. When the Hubble Space Telescope attempted to isolate the light from a single Cepheid, it inevitably scooped up the glare from neighboring stars. This stellar crowding meant the recorded brightness could be slightly skewed, which in turn threw off the calculated distances. If you multiply that tiny margin of error across hundreds of stars spanning the entire cosmic distance ladder, a noticeable bias naturally creeps into the final expansion rate. This exact reasoning was championed for years by George Fu alongside other veteran cosmologists. They argued that in such densely packed stellar environments, even Hubble's legendary optical resolution fell short. The light from individual Cepheids was constantly bleeding into adjacent stars, effectively polluting the data. If this crowding effect was the true culprit, the Hubble tension would simply evaporate. The expansion rates of the early and local universe would perfectly align, and the standard cosmological model would remain completely intact. Enter the James Webb Space Telescope, the ultimate tiebreaker. Equipped with a massive primary mirror and highly sensitive infrared instruments, Webb was specifically designed to pierce through cosmic dust. It possessed the unprecedented ability to distinguish individual stars within galaxies that older telescopes only saw as fuzzy smudges. If Hubble's Cepheid data was indeed compromised by stellar crowding, Webb was guaranteed to expose the flaw. Adam Rees and his research team immediately took on this monumental task. Rather than just double-checking a handful of Cepheids, they completely reevaluated roughly a third of Hubble's entire sample of distant galaxies. To ensure absolute accuracy, they anchored their calculations using the galaxy NGC 4258, whose distance is already confirmed through a completely independent measurement technique. They meticulously cross-checked every single data point. Furthermore, they didn't just rely on one approach. They deployed three distinct measurement methods. First, they used the traditional Cepheid variable technique. Second, they utilized carbon stars. Third, they measured the tip of the red giant branch, which focuses on the brightest stars in older galactic populations. Running these three independent methodologies on the exact same Webb dataset yielded a striking consensus. The data from all three methods aligned beautifully. Webb's new measurements matched Hubble's original figures to within a mere 2%. To put that in perspective, the actual Hubble tension represents a massive 8 or 9% gap. By confirming that the local universe is genuinely expanding at approximately 73 kilometers per second per megaparsec, Webb effectively validated Hubble's original numbers. Rees perfectly summarized this paradigm-shifting conclusion, noting that with instrumental errors officially ruled out, we are left with the thrilling and very real possibility that our fundamental understanding of the universe is flawed. In plain English, the telescopes work perfectly, the observational methods are solid, but the underlying mathematical framework connecting them is fundamentally broken. Meanwhile, Wendy Friedman from the University of Chicago spearheaded a separate research group to conduct her own comprehensive Webb analysis, also utilizing three distinct stellar classifications. Her findings introduced a fascinating twist to the narrative. Two of her three stellar indicators produced an expansion rate that perfectly matched the early universe predictions. However, the third indicator, the very same Cepheid variables used by Rees, yielded the higher local expansion rate. Friedman deduced that this discrepancy between the different stellar methods likely points to a hidden systematic error within one specific distance measuring technique, rather than a flaw in cosmology itself. Rees naturally pushed back against this conclusion. Adding to the fray, Nobel laureate Saul Perlmutter reviewed Friedman's preprint and noted that her findings actually imply a tension existing strictly within the star-based measurement methods themselves. The scientific debate is fiercely alive, fueled by incredibly precise numbers and conflicting techniques. Yet, the most fascinating aspect of this ongoing argument is the glaring absence of a specific excuse. Absolutely no one is seriously claiming that the Hubble tension is just a simple measurement mistake anymore. That convenient way out is completely dead, and Webb is the telescope that buried it. The reality replacing it is much more difficult to accept. We are now forced to conclude that either the standard cosmological model is missing a massive, fundamental ingredient, or the universe is engaging in some bizarre behavior that we simply lack the vocabulary to describe. Honestly, it could be a combination of both. It is worth remembering that Rees was a key member of the team awarded the 2011 Nobel Prize for the discovery of dark energy, an entirely unpredicted force that ultimately comprises the majority of our universe. He has already navigated one massive scientific revolution, and now he is watching a second one rapidly approaching on the horizon. But while the brightest minds in cosmology were fiercely debating expansion rates, Webb was busy staring into seemingly empty patches of the ancient sky, uncovering something completely unpredicted. The initial detections looked like mere visual noise, tiny, faint, reddish specks sprinkled across Webb's deep field imagery. Astronomers originally brushed them off as unusually tinted, dust-obscured distant galaxies, treating them as mundane background details to be catalogued and ignored. However, researchers soon realized just how incredibly abundant and visually bizarre these objects truly were. Affectionately dubbed little red dots, by the scientific community. Because astronomers truly appreciate straightforward naming conventions, these objects are astonishingly compact. They span a maximum of just a few hundred light-years across. To visualize that scale, consider that our Milky Way stretches roughly 100,000 light-years. Comparing a little red dot to our galaxy is like comparing a single marble to a massive sports stadium. Their intense, deep crimson glow indicates that they are either heavily shrouded in thick cosmic dust or situated so incredibly far away that their light has been severely redshifted by the universe's expansion. What makes them truly shocking is their sheer population density within Webb's deep fields. In certain early universe samples, 3 to 4 out of every single 100 galaxies fit this exact profile. This isn't a rare cosmic anomaly, it is a ubiquitous phenomenon. Chronologically, they suddenly pop into existence around 600 million years after the Big Bang, reach their absolute peak population at the 800 million year mark, and then almost entirely vanish by the time the universe is 1.5 billion years old. Regardless of their true nature, these objects experienced a definitive beginning, a dominant reign, and a sudden end. They represent a fleeting, previously unknown geological era of the cosmos that remained completely hidden until Webb finally pulled back the curtain. The initial leading theory suggested these dots were active galactic nuclei, essentially miniature galaxies harboring rapidly growing supermassive black holes. As these black holes voraciously consume surrounding gas, the material would heat up and release colossal amounts of radiation, perfectly explaining their intense brightness despite their tiny physical footprint. However, the classic observational signatures of active galactic nuclei were conspicuously absent. There was no distinct X-ray emission, no significant brightness variability over time, and no flat infrared spectrum. Visually, these dots exhibited a confusing hybrid nature, looking like quasars in certain wavelengths while mimicking pure starlight in others. The plot thickened when Dale Kosofsky and his research team detected incredibly high-velocity gas swirling around several of these dots, clocking in at speeds between 2,000 and 4,000 kilometers per second. While such extreme motion is highly unusual for standard galaxies, it is a hallmark of matter orbiting a growing black hole, whipped into a frenzy by the immense gravitational pull of a massive central object. Consequently, the scientific consensus shifted once more. Perhaps these dots were indeed powered by black holes, but of a completely unprecedented variety, compact, deeply hidden, and enveloped in just enough dense material to completely muffle their X-ray emissions. However, the sheer volume of these dots quickly morphed into the next massive headache. If every single one of them housed a supermassive black hole, the infant universe must have manufactured a staggeringly enormous population of these cosmic monsters in record time, vastly exceeding the predictions of standard cosmological models. Some clever researchers began connecting these little red dots to the broader mystery of those impossibly massive early galaxies. Perhaps the unexpectedly heavy galaxies and the little red dots were two sides of the same coin. Both anomalies pointed toward a population of black holes that ballooned in size far faster than theoretical physics should allow, strongly suggesting that our recipe for the early universe was missing a crucial ingredient. Seeking answers, a Harvard team led by Fabio Pacucci put forward a compelling explanation. They theorized that these dots could naturally form within dark matter halos possessing exceptionally low spin. In these slowly rotating halos, gas would be permitted to collapse directly inward, effortlessly creating the dense, compact, red light sources Webb was observing. The mathematical models aligned quite nicely with the telescope's actual observations. Other research groups took this concept even further, proposing that these dots might actually be the visible signatures of primordial black holes. Instead of forming from the collapse of dying stars, these entities would have been forged directly from the chaotic energy of the early universe itself. The little red dots had suddenly transformed into a gateway for a much more profound inquiry. Where exactly did the very first black holes originate? The answers continuously looped back to a radical concept that traditional cosmology had quietly swept under the rug. Perhaps black holes didn't form from stars at all. Perhaps the black holes actually came first. Arguably, the most baffling characteristic of the little red dots isn't their sudden appearance, but rather their abrupt disappearance. Astronomical surveys spanning the era from 600 million to 1.5 billion years post-Big Bang find these objects absolutely everywhere, populating field after field and image after image. Yet, right around that 1.5 billion year threshold, their population drastically plummets. Within just a few 100 million additional years, the little red dots are practically extinct. In cosmic terms, that is an incredibly sharp and sudden boundary. Whatever these objects truly are, they represented a specific phase, a distinct chapter in cosmic history. Something definitively switched them on, and something else definitively switched them off. The most straightforward explanation is that they simply evolved into a different type of object. Their gas was blown away, their dust cleared out, and these compact entities expanded and brightened to resemble the more familiar galaxies we see today. In this view, the dots didn't exactly vanish, they just graduated and transformed. While that evolutionary narrative satisfies certain observations, it directly clashes with others. Consider the massive quiescent galaxies, the elderly, retired veterans of the cosmos that sit quietly in our local universe. If the little red dots evolved into anything, these dormant giants are the most logical candidates. Recent findings from a Webb initiative known as the Rubies program, spearheaded by Anna de Graaf and Gabriel Brammer, indicate that early quiescent galaxies might have been severely undercounted in the past. Their work bumped the number of confirmed massive, resting galaxies up by roughly a factor of 10. Conversely, other scientists see a much darker scenario. They argue that the little red dots could be the leftover remnants of a completely isolated cosmic process, one that fails to connect smoothly with any later galaxy populations. In this view, they represent a class of objects with absolutely no surviving cosmic relatives, essentially a dead, extinct branch on the grand tree of cosmic structure. The lingering X-ray puzzle only serves to deepen this enigma. Traditional active galactic nuclei are notorious for blasting out massive quantities of X-rays, yet the little red dots are overwhelmingly X-ray quiet. A tiny fraction have exhibited faint X-ray signals, with one specific object, cataloged by NASA's Chandra Observatory under a lengthy technical designation, sitting perfectly atop the location of a Webb little red dot. Its X-ray energy profile closely mimics a quasar, a match reported in late 2025 that stands as one of the most robust links connecting these dots to supermassive black hole activity. Nevertheless, the vast majority of dots remain stubbornly dark in the X-ray spectrum. Their overall light spectrum resembles a black hole consuming gas in certain aspects, compact star formation in others, and something entirely absent from textbooks in the rest. To reconcile this, a fascinating concept known as the black hole star has been developed by researchers analyzing this exact data. This theory paints a truly striking picture. The dots aren't galaxies in any traditional sense. Instead, they are colossal, ultra-dense clouds of gas harboring a rapidly growing supermassive black hole hidden deep within their core. The surrounding gas acts as a shield, absorbing the X-rays and explaining their absence. Meanwhile, the star-like spectrum is simply the gas itself, illuminated and glowing fiercely from the immense energy radiating from the central black hole. Picture a single star the physical size of an entire galaxy, with a supermassive black hole serving as its beating heart. If this black hole star hypothesis holds true, the little red dots represent a highly specific, transient cosmic stage. They capture a fleeting moment when supermassive black holes were actively assembling inside dense gas clouds, right before those clouds dispersed to reveal the monstrous black holes within. Once the gas was blown away, these structures transitioned into standard galaxies with active centers. The dots seemingly disappeared because they were merely a transitional phase, a remarkably brief window in cosmic time offering a sneak peek at the exact moment supermassive black holes were being constructed. Webb managed to capture this because its infrared vision could pierce the veil that blinded every other instrument. If this theory is accurate, these dots are the closest thing astronomers possess to a baby picture of a supermassive black hole, the exact type of entity anchoring nearly every modern galaxy, including our very own Milky Way. Their rapid formation has baffled scientists for decades, but Webb might have just thrown open the doors to the cosmic maternity ward. The term black hole star inherently sounds like an oxymoron. After all, black holes notoriously devour light, while stars actively produce it. How can a single entity be both? The secret lies entirely in geometry. A black hole star isn't a single, solid object. It is a complex, layered system. At its very center sits a growing, supermassive black hole, completely enveloped by a gargantuan cloud of gas. As this gas spirals inward, it releases tremendous gravitational energy in the form of heat and light, shining brilliantly across the cosmos. When viewed from vast distances, the entire system simply looks like a massive, glowing sphere of gas, essentially a star, with the black hole completely concealed inside. The physical numbers involved are absolutely mind-boggling. Some of these proposed black hole stars span several hundred light-years in diameter. The encompassing gas cloud boasts a mass millions of times greater than our Sun, while the central black hole itself may already weigh anywhere from 100,000 to several million solar masses. And remember, all of this is happening a mere 600 million years after the Big Bang. For a quick reality check, the supermassive black hole anchoring our own Milky Way, known as Sagittarius A, weighs in at about 4 million solar masses, and it has had roughly 13 billion years to slowly grow. The black hole stars captured in Webb's imagery are achieving remarkably similar masses in less than a single billion years. Under the rules of normal physics, there simply isn't enough time for this to happen. Black holes typically grow by steadily pulling in surrounding matter, but the intense radiation generated by this infalling material pushes back outward. This creates a natural cosmic speed limit known as the Eddington limit. Once this threshold is reached, the outward radiation pressure perfectly balances the inward gravitational pull, preventing the black hole from consuming matter any faster. To explain the existence of these impossibly massive early black holes, scientists have brainstormed several clever workarounds to bypass this speed limit. Some researchers argue that these early black holes simply shattered the limit, accreting matter at super Eddington rates during brief, intense bursts. Others propose that these early black holes started out exceptionally large, bypassing the slow stellar collapse phase entirely by forming directly from the catastrophic collapse of colossal gas clouds. These heavy seeds would be born weighing between 10,000 and 100,000 solar masses, massive enough to skip the sluggish early growth stages altogether. Then, we arrive at the most radical proposition of all. The early black holes didn't form from gas clouds at all. Instead, they were forged during the very first chaotic moments of the universe itself. These are known as primordial black holes. Originally theorized by Yakov Zeldovich and Stephen Hawking back in the 1960s and 1970s, the concept suggests that during the extreme, chaotic conditions of the first second following the Big Bang, incredibly dense pockets of energy could have collapsed directly into black holes. While some of these would have been microscopic and evaporated eons ago, others could have been remarkably massive, surviving to this day and hiding quietly among the galaxies. If these primordial black holes genuinely exist, they could have acted as the ultimate foundational seeds for early galaxies. Imagine dropping a 1,000 solar mass primordial black hole into a region of ultra-dense gas at a high redshift, surrounding it with a dark matter halo, and allowing it to feed at extreme rates. Under those conditions, you could easily construct a 100 million solar mass black hole within just a few 100 million years. That specific timeline perfectly matches the exact phenomena Webb is currently observing. The underlying mathematics have been rigorously validated by multiple independent research teams. A notable paper authored by Xiangcheng Shen and his colleagues at the Hong Kong University of Science and Technology utilized a Bayesian framework to model exactly how primordial black holes could account for the high redshift galaxies discovered by Webb. Their preferred theoretical model aligned cleanly with the actual observations. Furthermore, another paper by A.D. Dolgov, expanding upon a 30-year-old conjecture developed with Joseph Silk, argued that supermassive primordial black holes could naturally serve as the seeds for both the early galaxies spotted by Webb and the supermassive black holes residing at the hearts of modern galaxies today. The ultimate implication of this theory is truly staggering. If our standard narrative regarding black hole formation is fundamentally incorrect, then nearly every single galaxy in the observable cosmos might be built around a primordial seed, an entity vastly older than the very first star, a relic that actively helped sculpt the grand structure of the universe before physical structure even truly existed. To find proof of these ancient seeds, scientists needed to look beyond infrared light. The next major breakthrough actually arrived in X-rays. Enter the Chandra X-ray Observatory. Launched by NASA in 1999, this spacecraft might be smaller and less famous than Webb, but it observes a completely different spectrum. X-rays are generated by extreme environments like superheated gas, exploding stars, and matter spiraling into neutron stars or black holes. Over its decades in orbit, Chandra has built an archive mapping millions of these high-energy sources. Naturally, once Webb started spotting those mysterious little red dots, researchers immediately cross-referenced their locations with Chandra's catalog. The vast majority came up empty, with the dots remaining stubbornly silent in X-rays. But then, they struck gold. Deep within a heavily observed sky region known as the extended growth strip, they found a perfect overlap. An X-ray source, previously logged under a lengthy technical name from the All-Wavelength Extended Growth Strip International Survey, sat in the exact same spot as a Webb little red dot. Amazingly, this emission was recorded years before anyone knew the red dot existed. Energy signature perfectly matched what we expect from quasars. These are incredibly luminous galaxies driven by highly active supermassive black holes, often sparked by galactic mergers. Discovering a quasar-style X-ray beacon right on top of a minuscule early universe red dot was a massive puzzle piece. Published in late 2025, this finding heavily reinforced the idea that supermassive black holes power these little red dots, even if most appear completely dark in X-rays. That single detection implies X-rays are indeed generated but blocked before reaching us. Thick dust, dense gas clouds, or a black hole star's outer envelope swallow the high-energy light. In this one case, X-rays simply leaked through a thinner gas patch. For other dots, the wrapping is too dense, hiding their inner beasts from Chandra. While Webb easily picks up the cloud's warm glow, Chandra cannot pierce through to the core. It is an elegant setup, a black hole tucked inside a cloud, generating energy that makes the cloud shine while staying invisible to X-ray telescopes. Think of a campfire wrapped in a heavy blanket. You feel the radiating heat, but cannot see the actual flames. This breakthrough does more than validate one theory. It paves the way for future discoveries. As astronomers point X-ray telescopes at more dot positions, they hope to catch additional leaks, offering direct proof of concealed black holes and helping separate black hole stars from alternative explanations. However, this raises a tricky question. If the early universe had black hole stars, why do we not see obvious ones today? The straightforward answer is that those surrounding gas clouds were temporary. Eventually, the material blew away, revealing the central black holes as standard active galactic nuclei or quasars. The black hole star phase ended once the cosmos thinned out too much to hide these monsters. It is a tidy story, but perhaps a bit too tidy. Some researchers note the observed transition from little red dots to normal galaxies is not as clean as this basic model predicts. Certain dots persist longer than expected, while others display spectral features matching neither a pure black hole star nor a pure galaxy template. This suggests the category is far more diverse than early discoveries implied, and Webb is far from finished. Upcoming surveys will catalog thousands of new dots, spectrographs will pull apart their light into chemical fingerprints, and X-ray follow-ups will hunt for more leaks. For now, these little red dots remain one of the most surprising discoveries in modern astronomy. Completely unpredicted and appearing in nearly every deep field, they challenge standard galaxy formation models and may rewrite the story of how supermassive black holes came to be. While astronomers debate the true nature of those little red dots, a separate sky region revealed 300 additional bizarre anomalies. At the University of Missouri, astronomy professor Hao-Jing Yan and his team tackled a straightforward inquiry. Exactly how many overly luminous bodies appear in Webb's deep space infrared pictures when they really shouldn't be shining so intensely? The researchers initially anticipated finding just a small handful of optical illusions that would eventually resolve into ordinary galaxies. Instead, they uncovered 300 distinct targets across Webb's observation zones, all radiating far more energy than standard models permit. Each represents a potential primordial galaxy burning much hotter than current formulas dictate. The team officially released these findings in 2025. Maintaining scientific caution, Yan labeled these discoveries as mere candidates. He emphasized that confirming even a tiny fraction as genuine early galaxies would severely disrupt our understanding of primordial cosmic evolution. The margin for error is truly razor-thin. This extreme luminosity circles back to a recurring dilemma. For ancient galaxies to shine this fiercely, they must either generate stars at an impossibly frantic pace or harbor non-stellar light sources. Both scenarios shatter the conventional framework, forcing us to overhaul stellar birth theories or accept that the infant cosmos contained unidentified elements. These 300 bodies share several key characteristics. They are compact and reddish, hinting at heavy dust reddening or vast cosmic distances. Their infrared emissions also drastically exceed older forecasts. While some might be little red dots, others could represent an entirely separate class. Pinning down their identities is incredibly slow. As Yan noted, space identification demands rigorous spectroscopy, extensive follow-up scans, intense peer debates, and the systematic elimination of alternatives. Scientists will scrutinize these candidates for years. Some will prove to be foreground bodies accidentally superimposed over the distant past, while others will be exposed as active galactic nuclei masquerading as bright galaxies. However, a select few will likely pass every test as verified primordial enigmas. Even if just 10% survive, that adds 30 genuine anomalies to the growing inventory of early universe phenomena defying predictions. Ultimately, the broader trend matters most. Webb continuously detects overly brilliant structures existing far too soon across independent surveys and methodologies. Accumulated together, these findings form an undeniable reality. Questioned about this pattern, a veteran cosmologist coined a term now spreading through the community: excess light. The infant universe generated significantly more illumination than our standard recipe permits. Whether this surplus originates from radiant stars, ancient black holes, dark matter collisions, or something unimagined, the evidence highlights a missing ingredient. That phrase has become a constant echo in modern astrophysics. We need a missing ingredient to solve the Hubble tension, explain early bright galaxies, understand little red dots, and potentially fix rotation asymmetry. Examining these four open mysteries, researchers wonder if a single hidden component fixes them all, or if each puzzle requires its own unique solution. Both scenarios are deeply unsettling. One universal missing piece would revolutionize physics, while multiple distinct missing pieces would be profoundly humbling. Our cosmic recipe was supposed to consist of a few basic elements. Now, it resembles a messy kitchen drawer filled with mysterious, unlabeled jars. Peering into that messy kitchen drawer of cosmic mysteries reveals one last massive twist regarding those brilliantly bright early galaxies. This puzzle digs much further down than mere ingredients, expansion tensions, or galactic spins. Believe it or not, a few of these stellar islands actually appear to predate the cosmos itself. Hearing that feels like a total paradox. After all, basic math dictates that nothing contained within our 13.8 billion-year-old universe could possibly exceed that age limit. Despite this straightforward logic, the James Webb Space Telescope has captured ancient structures with calculated ages that awkwardly push against, or even shatter, that ultimate deadline. Scientists arrive at these numbers by studying the specific chemical makeup and star clusters within these distant objects. Ancient stars leave behind distinct light fingerprints, and forging heavy elements is a slow process demanding multiple generations of stellar birth, death, and rebirth. By evaluating metal abundance alongside stellar ages, experts calculate the total duration of star formation. Shockingly, Webb's data sometimes suggests this timeline stretches far beyond the moments elapsed since the Big Bang. Naturally, nobody claims these objects actually broke causality by existing before time began. Instead, a crucial link in our measuring tools must be flawed. We are either miscalculating distances, misjudging true ages, or misunderstanding cosmic expansion. This discrepancy has driven certain scientists to investigate unconventional theories. Enter Rajendra Gupta, a thinker who recently captured the spotlight by suggesting our cosmos is vastly older than commonly accepted. Through multiple studies, he posits the universe might actually be 26 to 27 billion years old, essentially doubling the accepted timeline. While that sounds absolutely wild, his step-by-step logic is thorough enough to demand attention. His framework merges two distinct concepts. First, he introduces varying coupling constants, suggesting fundamental rules like light speed and gravitational pull might subtly drift over billions of years, altering how we translate redshift into distance. Second, he revives the vintage, tired light hypothesis, proposing that light particles simply exhaust their energy during long journeys, naturally reddening without spatial expansion. Mainstream science largely discarded tired light because it fails to explain the cosmic microwave background, galaxy clustering, and supernova dimming, which all point to genuine spatial stretching. However, Gupta insists blending tired light with drifting constants perfectly aligns with all data, creating an older cosmos where Webb's highly evolved galaxies fit perfectly because they had extra time to develop. Even more astonishingly, his model completely eliminates the need for dark matter. This is a massive assertion, considering invisible matter has served as the foundational scaffolding for modern astrophysics for decades. Erasing it might clear up a few headaches, but would trigger an avalanche of new problems. Unsurprisingly, most experts remain highly doubtful. Our current standard model has survived rigorous testing against a massive variety of phenomena. We see dark matter fingerprints everywhere, from galaxy rotation curves and gravitational lensing to the microwave background and cosmic structure. Ditching it means inventing brand new explanations for every single one of those effects. Still, the undeniable presence of these fully formed ancient structures leaves the door cracked open. Whenever traditional physics hits a wall, alternative models get a chance to speak. To defend the status quo, mainstream astronomers are searching for tweaks to save the current paradigm. Perhaps the first stars burned much brighter than assumed, ancient black holes acted as rapid growth seeds, or tricky dust distributions created an optical illusion of advanced age. While every patch sounds reasonable, not a single one has achieved total consensus. Ultimately, these impossibly old galaxies serve as both a fascinating hint and a glaring red flag. Perched right on the boundary of modern understanding, they force investigators to wonder if we need to overhaul the entire cosmological rulebook, rather than just tweaking minor details. This brings us to a fascinating new chapter, because if the cosmos itself is fundamentally different from our expectations, then its core components, like the invisible mass dominating it, might also be completely misunderstood. Enter Rajendra Gupta and his proposition of an older cosmos, a theory heavily reliant on a concept most physicists dismiss as a mere mathematical quirk. We are talking about the fundamental constants of nature. These supposedly unchangeable values dictate the behavior of the entire universe. You probably know the famous ones: the speed of light, gravitational strength, and the electron's charge. They are the ultimate rulebook for matter. Thanks to these specific numbers, atoms stay intact, stars ignite, and light zooms through the void at its exact, measured pace. The bedrock assumption in physics is that these values have remained locked in place since the Big Bang. Space might be stretching, and galaxies might be flying apart, but the underlying physics never shifts. A meter stays a meter, a second remains a second, and a kilogram is always a kilogram, regardless of where or when you measure them. However, the covariant coupling constants hypothesis, often abbreviated as CCC, directly challenges this rigid viewpoint. It explores the possibility that these foundational numbers might actually fluctuate slightly over cosmic history, shifting in a synchronized manner to maintain a deeper, hidden balance. Gupta's specific model allows multiple constants to drift in unison. This clever trick ensures that measurable phenomena, such as the light emitted by stars or the spectral lines of atoms, still align with our observations, even as the foundational numbers slowly tick away from their original values. Naturally, the majority of the physics community views this as a massive long shot. Researchers have spent decades running rigorous experiments to detect any such drift, establishing incredibly strict boundaries. By studying ultra-precise atomic clocks, analyzing the light from distant quasars, and examining the remnants of ancient natural nuclear reactors right here on Earth, scientists have boxed in these constants tightly. If any shifting is happening, it is minuscule. Yet, minuscule does not equal zero. When you stretch those tiny fluctuations across 13 billion years, the accumulated impact becomes substantial. A slight tweak in gravity's strength would alter how quickly galaxies clump together. A minor shift in light speed would completely redefine the math connecting distance and travel time. When several constants drift in harmony, the total impact on our cosmic yardsticks could be massive. Gupta asserts that blending these drifting constants with the vintage tired light concept creates a beautifully consistent universe. This hybrid approach perfectly accommodates the James Webb Space Telescope's stunning discoveries without contradicting our older datasets. In this view, those distant galaxies appear fully formed simply because they actually are fully formed. We aren't miscalculating their mass, nor are we misreading their redshift. The cosmos just had a much longer runway to construct them. Where does this extra time come from? It stems from a radical reimagining of galactic redshift. Traditional cosmology views redshift purely as the stretching of space. Gupta, however, divides it into two distinct mechanisms. A portion of the redshift genuinely comes from cosmic expansion, but another portion results from photons gradually bleeding energy as they trek across the void, the classic tired light effect. If expansion is only responsible for a fraction of the redshift we observe, our entire timeline shifts. The mathematical bridge between distance and time is rebuilt, pushing the universe's origin much further back. Just how far back? Gupta's published research suggests an age of roughly 26 to 27 billion years, effectively doubling the accepted timeline. While that number sounds absolutely wild by conventional standards, his framework elegantly solves a major headache. Those impossibly mature early galaxies suddenly make perfect sense. They simply had ample time to evolve. Their heavy elements and massive sizes aren't bizarre glitches. They are the natural results of star formation continuing for billions of years, longer than the standard model permits. Unsurprisingly, mainstream astronomers have pushed back hard against this notion. Skeptics emphasize that an ancient universe with shape-shifting constants would leave undeniable fingerprints all over our data. The atomic signatures from primordial quasars would look wrong. The intricate patterns within the cosmic microwave background would fail to match our standard forecasts. Even the primordial ratios of chemical elements would be completely out of whack. While Gupta and his team insist their equations can absorb these constraints, their detractors vehemently disagree, sparking lively debates in peer-reviewed journals. Thanks to Webb's baffling data, however, these discussions have graduated from obscure internet forums to the main stages of professional astronomy conferences. The telescope essentially kicked open a door that had been sealed shut for nearly a century. Back in the 1920s, while Edwin Hubble was busy proving that space was expanding, a Swiss astronomer named Fritz Zwicky offered a competing vision. He suggested that distant galaxies weren't actually retreating from us. Instead, their light was simply getting exhausted during its epic journey. The logic was quite elegant. As photons crossed unimaginable distances, they might surrender a bit of energy by interacting with the fabric of space or unseen matter. Dropping energy translates to a lower frequency, which shifts the light toward the red end of the spectrum. This mimicked the exact signature of an expanding universe. Over the ensuing decades, though, Zwicky's hypothesis was thoroughly tested and ultimately discarded. Phenomena like the cosmic microwave background, the dimming of faraway supernovae, and the specific time-stretching seen in exploding stars all perfectly matched genuine cosmic expansion. Tired light simply couldn't juggle all those observations at once. By the 70s, the Big Bang and expanding space had claimed total victory, relegating tired light to a cautionary tale in physics textbooks. Today, Webb has breathed new life into this old conversation. Researchers aren't dusting off Zwicky's exact original blueprint, which still trips over those classic hurdles. Instead, they are developing modernized, hybrid versions, often paired with concepts like covariant constants, designed to patch the original flaws while keeping the core premise alive. The driving motivation remains identical to the one from a century ago. If the standard expansion model clashes with our telescopic reality, we must re-examine the alternatives. The biggest hurdle for tired light has always been the cosmic microwave background. This faint, ubiquitous radiation sits at about 2.7 Kelvin and forms a flawless thermal curve. Standard physics beautifully explains this as the cooled, stretched afterglow of the Big Bang. Tired light struggles immensely here, because photons losing energy via scattering would blur that perfect thermal spectrum into a messy smear. Modern advocates try to bypass this by strictly defining how and when this energy loss occurs, perhaps limiting it to specific light wavelengths or particular eras of cosmic history. Naturally, every new tweak makes the theory more convoluted, stripping away the elegant simplicity that made it so appealing initially. Then there is the supernova challenge. Faraway stellar explosions appear to fade in slow motion compared to local ones. Standard physics attributes this to time dilation, a core feature of Einstein's relativity, where expanding space literally stretches the perception of time. In its purest form, tired light predicts zero time dilation. Distant supernovae should just look redder and dimmer, not slower. Because we clearly observe this slow motion effect, the supernova test originally killed the tired light concept. Yet the sheer shock of Webb's ancient galaxies has created enough friction within the standard model that scientists are willingly resurrecting these partially debunked concepts. If a blended model featuring a tiny dash of tired light can neatly explain those early mature galaxies, it deserves a seat at the table, regardless of its other baggage. To be completely transparent, the astronomical establishment has not warmly welcomed tired light back into the fold. Papers championing it still dwell on the fringes, sparking curiosity but failing to build a consensus. While Webb's findings certainly make the standard model sweat, most experts believe the solution lies in modifying the current paradigm, not trashing it entirely. Tired light remains a distinctly minority opinion, serving more as a symptom of cosmology's current growing pains rather than a victorious new paradigm. Those impossibly old galaxies might ultimately be explained by clever dust distributions, unusually bright early stars, primordial black holes, or something we haven't even imagined yet. The true takeaway is that when the universe refuses to cooperate with our theories, no historical idea is off-limits. Let's indulge Gupta's framework for a moment and imagine the universe really is 26 or 27 billion years old. The ripple effects would be monumental. First, the entire schedule of cosmic construction gets rewritten. Galaxies require immense time to build themselves, starting as dark matter halos that pull in gas, spark stellar nurseries, and collide with neighbors. The standard model allocates roughly 13.8 billion years for this entire process. When Webb reveals fully formed galaxies just a few hundred million years after the Big Bang, that schedule breaks down. But if you double the universe's age, the tension vanishes. Those ancient galaxies suddenly have 13 billion years of hidden history to grow and mature before they enter our telescopic view. They look old because they genuinely are old. The second massive shift involves dark matter. In conventional physics, this invisible substance acts as the gravitational scaffolding that accelerates galaxy formation, preventing the expansion of space from ripping gas clouds apart before stars can birth. Gupta's extended timeline, combined with his shifting constants, boldly claims to replicate this rapid galaxy formation without needing any dark matter whatsoever. In his view, a slow-revolving cosmos with subtly altered physics naturally achieves what dark matter does in the standard model. If this mathematical tightrope walk actually holds up across all scales, dark matter could be relegated to the historical dustbin alongside phlogiston, the mythical fire element, and the luminiferous ether, the imaginary medium once thought to carry light. Both were discarded when better theories arrived. However, that is a colossal if. The vast majority of evidence still heavily favors dark matter's existence. Even though underground detectors haven't caught a direct particle yet, its gravitational footprints are unmistakable in galactic rotation speeds, the bending of light around massive clusters, and the cosmic microwave background. Gupta's theory must flawlessly explain all these phenomena without his invisible scaffolding, a feat critics insist is impossible, while supporters fiercely defend. The math is incredibly dense, and the broader community remains highly skeptical. Finally, an older universe radically alters our predictions for the cosmic finale. The ultimate heat death, where everything fades into a freezing, uniform void, would unfold on a vastly different schedule, and the current accelerated expansion phase might operate under different rules. While highly speculative, treating Gupta's ideas as a grand thought experiment is incredibly valuable. It forces physicists to ask what happens if our foundational timeline is flawed. The universe's age isn't just a trivial detail. It is the bedrock of almost every cosmological calculation. Alter it, and everything else must be reevaluated. Most scientists aren't prepared to take that leap, as the 13.8 billion-year figure has conquered countless observational hurdles, especially regarding the cosmic microwave background. Nevertheless, those impossibly mature galaxies are whispering a radically different timeline. The James Webb Space Telescope has captured that whisper, and whether it evolves into a roaring paradigm shift or fades into silence is the defining question of the next decade. That whisper is growing louder among researchers suspecting dark matter might be entirely fictional, and Rajendra Gupta is far from the only voice in this chorus. A dedicated minority has questioned this invisible mass since the 1980s, when Mordechai Milgram introduced modified Newtonian dynamics, or MOND. His core concept suggests gravitational rules change under extremely low accelerations, naturally copying the pull we attribute to dark matter without needing hidden particles. MOND has scored impressive victories over the years. It beautifully maps specific galaxy rotation speeds, frequently outperforming traditional dark matter frameworks that rely on tweakable variables. However, the theory stumbles hard at the massive scale of galaxy clusters, where MOND's predictions completely miss the mark compared to actual gravitational lensing observations. The realm of alternative ideas remains absolutely packed. From tweaked gravity and tired light concepts to models featuring shifting universal constants, every proposal brings unique defenders and detractors. Yet, all share a deep unease with mainstream cosmology. The accepted narrative says regular atoms account for merely 5% of existence, while dark matter claims 27% and dark energy dominates with 68%. This means our instruments cannot see a staggering 95% of reality. Many experts feel a model where almost everything is mysterious is fundamentally flawed. Arguing these puzzles highlight a broken framework rather than undiscovered physics. The hunt for dark matter has now stretched past 3 decades. Deep underground labs, heavily shielded against cosmic radiation, wait for faint collisions between normal atoms and phantom particles. Atom smashers hunt for exotic matter, while telescopes scan for the radioactive fallout of dark matter destroying itself. Despite this, we have caught absolutely nothing. The weakly interacting massive particle, once the undisputed favorite, has been systematically eliminated across a vast spectrum of potential sizes. Fresh candidates keep popping up, but testing them demands increasingly extreme technology. This endless dry spell makes many wonder if we are chasing the wrong ghost entirely. What if dark matter is not a novel particle, but a vast swarm of ancient, primordial black holes? Such objects would effortlessly evade current detectors. This is exactly where Webb's discoveries of early black holes crash into the dark matter debate. If the early universe spawned enough primordial black holes, they could easily supply the missing mass. Furthermore, they would perfectly explain how Webb sees supermassive black holes growing so impossibly fast. Two massive puzzles, one elegant solution. Multiple scientific teams have already crunched the numbers. A study guided by researchers like Yifu Kai investigated if ancient black holes could act as both dark matter and foundational seeds for infant galaxies. They found certain mass ranges fit both roles, while others fall apart, leaving the debate open. Nevertheless, Webb's sightings of bright, dense early objects have injected fresh energy into this theory. Paired with our total failure to find dark matter particles, alternatives look much more appealing today. Figuring out if dark matter is a hidden particle, a black hole swarm, or an illusion from flawed physics is a monumental crossroads. The conclusion will dictate science for generations. Currently, traditional dark matter holds the crown, keeping rivals on the fringes. But thanks to Webb, those fringes are rapidly creeping toward the center. As those fringes creep inward, we have to look at how the very first stars actually came together in the dawn of the cosmos. These initial stellar furnaces didn't just ignite in isolation. Instead, they clustered along massive, invisible scaffolding that cosmologists refer to as the cosmic web. Think of it as a vast network of dark matter, threads stretching across the void, pulling in surrounding gas. This grand architecture dictates the entire evolution of the universe. Where these dark threads intersect, galaxies blossom. Where multiple strands cross paths, massive galaxy clusters take shape. And in the vast gaps between them, empty cosmic voids expand. Under the conventional cold dark matter framework, this universal scaffolding is incredibly lumpy. In this scenario, dark matter acts much like a sluggish gas made of slow-moving particles. Gravity causes these particles to bunch up into dense knots and thick filaments across every conceivable scale. The tiniest clumps collapse first, eventually crashing into one another to build progressively larger structures in a bottom-up hierarchy. Because of this specific growth pattern, the Standard Model makes very clear predictions about the physical appearance of the universe's oldest galaxies. They ought to be compact, somewhat round, and relatively faint. Over billions of years, these little spheres should swallow their neighbors, gradually flattening out into the majestic spiral disks we observe in the modern night sky. However, the James Webb Space Telescope has completely flipped this expectation on its head. A fascinating study spearheaded by Alvaro Pozo from the Donostia International Physics Center, alongside researchers from Harvard, MIT, and Arizona State University, took a deep dive into the morphologies of infant galaxies captured by Webb. Their analysis revealed a stunning surprise. A huge number of these ancient systems are dramatically stretched out. Instead of looking like neat little spheres or flat pancakes, they are highly prolate, resembling cosmic cigars or glowing American footballs. To figure out what on earth could create these bizarre structures, the research team fired up computer simulations to test 3 distinct dark matter flavors. First, they ran the standard cold dark matter model. Next, they tried warm dark matter, where particles zip around faster and blur out the tiniest cosmic structures. Finally, they tested wave dark matter, a bizarre concept where the dark sector is made of ultralight particles acting like giant quantum waves across the cosmos. The results were telling. The traditional cold model completely failed to generate these stretched-out galaxies in any meaningful quantity, but the warm and wave models nailed it. In those alternative simulations, the cosmic web was far less chunky, featuring smooth, sweeping filaments instead of dense clumps. As gas streamed down these gentle, elongated channels, it naturally pooled into the football-shaped infant galaxies we see today. This strongly hints that the dark sector isn't made of sluggish, clumpy particles after all, but rather something much lighter that exhibits wave-like quantum properties on a grand scale. Rogier Windhorst, an interdisciplinary web scientist and Regent Professor at Arizona State University, perfectly captured the gravity of this discovery. He pointed out that our traditional view of an expanding cosmos relies on galaxies slowly building up from tiny dark matter seeds that gather stars and merge through gravity. Yet, Webb's data implies that these primordial systems are actually nestled within distinct, stretched-out filaments. This specific environment perfectly matches the theoretical predictions for an ultralight, quantum-behaving dark matter particle. It is a massive claim, though it is important to note that it doesn't outright declare the cold dark matter model dead. Rather, it simply highlights that Webb's actual observations align much more beautifully with an entirely different flavor of dark matter. The concept of ultralight, or fuzzy, dark matter isn't actually brand new. Theorists have been tossing the idea around for years. In this framework, the particles are astonishingly featherweight, boasting masses countless orders of magnitude tinier than traditional candidates. Because they are so light, their quantum wavelengths stretch out enormously, allowing them to ripple and flow like waves across the scale of entire dwarf galaxies. Naturally, actually catching one of these particles has been virtually impossible. They barely interact with regular matter, rendering them completely invisible to our underground direct detection traps. Consequently, scientists have had to rely on indirect clues, primarily studying how galaxies are born and change over time. Now, Webb has handed us a massive new piece of indirect proof, showing that the physical shapes of ancient galaxies completely defy cold, dark matter forecasts, while perfectly matching the warmer, wavier alternatives. Of course, defenders of the standard cold model aren't throwing in the towel just yet. They have plenty of reasonable counterarguments, suggesting that perhaps our telescope's selection biases are skewing the shapes we see, or that the computer simulations just need a bit more fine-tuning. They argue that minor tweaks to the standard paradigm might eventually recreate these stretched-out forms. Yet, the anomalies just keep stacking up. After a remarkably long and dominant reign, cold dark matter is finally facing its first genuine rival in years, and Webb just handed wave dark matter a massive boost. If you open a classic astronomy textbook, it will tell you that early galaxies should look like tiny, spherical gas clouds slowly bulking up through collisions. A billion years post-Big Bang, they should start flattening into disks, and by the 2 billion year mark, beautiful spirals should be everywhere. Instead, Webb is revealing a totally different reality: glowing cigars and stretched-out footballs that look more like squished beams of light than traditional star clusters. And as POSO's research highlights, these aren't just a few weird outliers. They represent a huge, dominant chunk of the galactic population during specific eras of the early universe. The conventional framework simply struggles to pump out these elongated structures in the sheer volumes we are observing. Because cold dark matter creates a highly fragmented, lumpy web, any galaxy growing inside those dense pockets naturally trends toward a roundish shape. To get a beautifully stretched galaxy, you absolutely need gas to flow smoothly down a long, narrow cosmic pipeline, which the clumpy standard model just can't reliably provide. Warm and wave dark matter, on the other hand, excel at this. They generate those sleek, smooth filaments, allowing infalling gas to stretch out and ignite into stars in a distinctly elongated pattern, perfectly mirroring Webb's football-shaped discoveries. Cosmologists have actually understood for a long time that the specific nature of dark matter should leave a unique fingerprint on galactic shapes. The historical roadblock was simply that our older telescopes couldn't see far enough or clearly enough to tell those fingerprints apart. The hints were there, but the data was frustratingly blurry. Webb completely shattered that limitation. Thanks to its incredibly crisp infrared vision, we can now clearly map out the exact physical structures of galaxies that existed less than a billion years after the Big Bang. We aren't looking at smudged pixels anymore. We are measuring precise orientations and axis ratios. In their study, Poso's group highlighted 6 specific galaxies to prove this point. They placed the actual Webb photos of these filament-embedded systems on the top row of their charts. Right below, they showed warm dark matter simulations that looked almost identical to the real thing. On the bottom row, they placed the cold dark matter simulations, which looked absolutely nothing like the actual telescope images. This stark visual contrast has convinced many experts that the standard model needs an update, not necessarily throwing cold dark matter in the trash, but seriously rethinking which dark matter flavor actually governs the high redshift universe. The fallout from this discovery reaches far beyond just the shapes of ancient galaxies. If the dark sector is genuinely warmer or wavier than we thought, the entire small-scale architecture of the cosmos changes. We would expect to see far fewer tiny dwarf galaxies. The inner cores of galaxies would be much smoother, and the way small galaxies rotate would shift dramatically. Astronomers are actively testing these ideas right now by surveying local dwarf galaxies to see if the missing satellites, predicted by warm and wave models, are actually absent. The debate is fiercely ongoing, with some local data backing the warmer models and other data defending the cold paradigm. However, Webb has undeniably pushed the scales in favor of the warm and wavy camp. If ultralight, quantum-behaving dark matter is real, the shockwaves will hit nearly every branch of physics. Our traditional favorite candidate, the weakly interacting massive particle, or WIMP, is thought to weigh about 100 times more than a single proton. An ultralight particle, however, would be 100 trillion times lighter than that. It is a staggeringly tiny mass, which gives these particles mind-bogglingly long quantum wavelengths that can stretch across light years. Instead of swarming like a cloud of tiny billiard balls, this dark matter would ripple and oscillate as one massive, continuous wave. This fundamentally alters how the dark sector clumps together. While cold dark matter collapses into incredibly tight, dense halos, wave dark matter creates fluffy, diffuse halos with remarkably smooth centers. Consequently, galaxies embedded in these fuzzy halos would have less concentrated middles and softer outer edges. Interestingly, we already see hints of this locally, where some dwarf galaxies feature flat central density profiles instead of the steep, dense spikes predicted by the standard model. Cosmologists call this the core cusp problem, where the cold model predicts a sharp cusp, but reality shows a flat core, a discrepancy that wave dark matter elegantly solves. On the flip side, the cosmic microwave background pushes back. This ancient afterglow of the Big Bang places incredibly strict limits on dark matter, meaning wave models have to be meticulously fine-tuned to avoid contradicting the CMB data. Some variations make the cut, while others fail completely. Catching these ultralight particles in a lab is a monumental challenge. They don't bounce off atomic nuclei, they don't emit any light, and they basically only interact via gravity. To find them, physicists are trying to detect their subtle wave-like ripples using ultra-precise instruments. For example, highly sensitive atomic clocks might tick at slightly altered speeds if an oscillating dark matter wave washes over them. So far, however, these lab experiments have come up empty. Almost all our constraints on wave dark matter come purely from astronomical observations, like galactic clustering and the cosmic web. Webb has just injected a powerful new pillar of evidence into this mix, showing that stretched-out infant galaxies and their filamentary homes make far more sense in a wavy universe than a cold, clumpy one. If wave dark matter ultimately claims victory, the physics landscape will be permanently altered. The beloved WIMP hypothesis would be relegated to the history books, and decades of expensive underground direct detection experiments would be viewed as fascinating historical artifacts. The scientific focus would aggressively pivot toward hunting for wave-like signatures, transforming cosmic-scale quantum mechanics from a quirky theoretical idea into a mainstream field of study. This paradigm shift wouldn't invalidate Einstein's general relativity, nor would it erase the Big Bang, but it would completely rewrite our understanding of everything that happened between those two monumental events. The fundamental makeup of the universe's matter, the exact mechanics of cosmic structure formation, and the inner workings of galactic halos would all be radically updated. Naturally, the majority of cosmologists are hesitant to embrace such a massive overhaul just yet. The standard cold dark matter model is supported by decades of robust, converging evidence, and dethroning it will require far more than a single intriguing telescope observation. But those intriguing observations are undeniably piling up. Webb has handed us several major clues, from the strangely elongated ancient galaxies to the puzzling density profiles of galactic cores. Combine those with the stubborn, ongoing failure to detect any heavy dark matter particles in our labs, and the concept of wave dark matter has officially evolved from a fringe speculation into a highly serious scientific hypothesis. But while wave dark matter tackles the invisible universe, another long-standing cosmic puzzle is forcing us to rethink the visible one, specifically how black holes are born. Traditionally, we are taught that black holes are the corpses of giant stars. When a massive star exhausts its nuclear fuel, gravity takes over, crushing the core into a stellar mass black hole. Give this process billions of years, and you end up with the vast population of ordinary black holes we see sprinkled throughout modern galaxies. However, when we look at supermassive black holes, monsters boasting millions or even billions of times the mass of our sun, the standard stellar collapse story completely falls apart. Stars simply cannot die and leave behind something that huge. To explain these behemoths, astronomers have long relied on a gradual growth model. The idea is that smaller seed black holes form first, then spend hundreds of millions of years gobbling up surrounding gas and colliding with one another to slowly bulk up. It is a slow, methodical process that requires a massive amount of cosmic time. Yet, the James Webb Space Telescope has completely shattered this timeline. Webb has peered back to just a few 100 million years after the Big Bang and found supermassive black holes already weighing in at millions of solar masses. The universe simply was not old enough for the traditional seed and feed method to have finished its work. Faced with this impossible timeline, scientists are dusting off a radical, decades-old escape route: primordial black holes. Unlike their stellar cousins, these ancient objects did not come from dying stars at all. Instead, they were forged in the chaotic, boiling environment of the very first second following the Big Bang. This concept actually traces its roots back to 1966 with Yakov Zeldovich and was further developed by Stephen Hawking in 1971. They realized that the infant universe was not perfectly smooth. It had microscopic density fluctuations. If a specific pocket of space happened to be just dense enough, it could bypass the star phase entirely and collapse straight into a black hole. Theoretical mass of these primordial black holes covers a mind-boggling spectrum. On the microscopic end, you could have tiny specks weighing a mere millionth of a gram, which would quickly vanish via Hawking radiation. On the other end, massive ones could survive to this day, hiding silently alongside normal matter. But the real game changers are the absolute giants, objects weighing thousands or even millions of solar masses, perfectly primed to act as the foundational seeds for the very first galaxies. For a long time, this idea sat on the absolute fringes of astrophysics. Without direct proof, and with stellar collapse seemingly doing a fine job explaining the black holes we knew about, there was no reason to clutter the standard model with hypothetical relics from the dawn of time. But Webb's impossible discoveries have completely rewritten the equation. We desperately need an explanation for these ancient supermassive black holes, and primordial seeds offer one of the most elegant solutions. For instance, a research team led by Zhijiang Shen at the Hong Kong University of Science and Technology recently published a paper suggesting that primordial black holes weighing roughly 1,000 solar masses could perfectly seed the early galaxies Webb is spotting. Using Bayesian analysis, their models strongly favor a log-normal mass distribution peaking right around 750 solar masses. If you drop these specific primordial seeds into dense gas clouds nestled within dark matter halos, let them gorge on gas at incredibly high rates, and allow them to merge, they will balloon into the supermassive monsters Webb observes in just a few 100 million years. The mathematics work out beautifully. offering a unified explanation for both the impossibly early galaxies and the giant black holes at their centers. This line of thinking strongly echoes the work of A. Dolgov from Novosibirsk State University, who has been championing similar ideas for years. Building on a 1990s collaboration with Joseph Silk, Dolgov has long argued that supermassive primordial black holes are the natural architects of early galaxies and quasars. Webb's stunning visuals have suddenly thrust this vintage hypothesis back into the spotlight. If these primordial objects truly exist, they act as a cosmic skeleton key, unlocking multiple mysteries simultaneously. They provide the necessary seeds for early supermassive black holes, supply the extra energy needed to ignite early bright galaxies, and might even serve as a viable candidate for dark matter itself. It is an incredibly tidy, unified picture, but it comes with a massive hurdle: detection. Because primordial black holes interact almost exclusively through gravity, they are practically invisible unless they are actively eating. They will not trigger our particle detectors, meaning we have to rely entirely on indirect gravitational clues. In a way, Webb is the very first tool powerful enough to spot these indirect signatures at the exact right moment in cosmic history. Going back to that early 1990s paper by Dolgov and Silk, they specifically proposed that these primordial black holes would form with a log-normal mass distribution. It was a highly technical concept that reached a tiny audience, quietly gathering dust in academic journals for 3 decades. In cosmology, most theoretical predictions outlive their creators because the universe is too vast and the required technology takes too long to build. But Dolgov and Silk were incredibly lucky. Their specific prediction was put to the test by Webb, and the log-normal mass distribution they theorized perfectly aligns with the exact seed masses required to grow Webb's early supermassive black holes. Making a highly specific prediction 30 years before the technology exists to verify it, and then having the data actually match, is the absolute gold standard of theoretical physics. While it does not definitively prove their theory, it skyrockets the probability that they are right. Dolgov has been quite vocal in his recent publications about this remarkable alignment, boldly stating that his 30-year-old idea not only saves the standard cosmological model, but actually predicted the rich tapestry of early galaxies and quasars Webb is now seeing. While there is certainly a bit of proud hyperbole in his words, the core of his claim holds water. The fit between his old math and Webb's new data is not absolutely flawless. It requires some tweaking, and some cosmologists still argue over the finer details. But the fundamental shape of his prediction is shockingly accurate. The actual mechanism Dolgov suggests for creating these black holes is also quite unique. Rather than simple density fluctuations, he proposes a highly complex interaction between matter and antimatter in the infant universe, which creates specific overdense pockets that selectively collapse. The physics is dense, but the outcome is a perfectly tailored population of black holes ready to build cosmic structure. Unsurprisingly, his paper is now being heavily cited in the post-Webb scientific community. Global teams are running complex computer simulations to see if his model can explain the entirety of Webb's findings. While some simulations show a great fit and others show friction, the final verdict is still out. What is undeniable, however, is that primordial black holes have graduated from a weird fringe theory to a mainstream scientific priority, thanks entirely to the platform Webb has provided. If we eventually confirm that these ancient objects seeded the first galaxies, the ripple effects will extend far beyond just black hole physics. Proving they formed in the first second of existence would give us an unprecedented window into the extreme energies, quantum fields, and fluctuations present at the literal birth of the cosmos. These black holes would essentially act as pristine fossils, carrying secrets from an era we have no other way to study. At this moment, the evidence is highly compelling, but not yet absolute. Webb's discoveries fit the primordial black hole models wonderfully, but they can also be squeezed into other theories with varying success. We will need the next generation of observatories, like the Roman Space Telescope and advanced ground-based arrays to finally separate the truth from the alternatives. As for Dolgov, who is now in his 80s, he might actually live to see his life's work either fully vindicated or completely debunked, a rare privilege in a field where theorists rarely see their grandest ideas tested. Webb has drastically fast-tracked this timeline. To truly understand why these heavy seeds are so necessary, we have to look at the cosmic speed limit for black hole growth. Black holes cannot just swallow matter instantaneously. As material spirals inward, it gets incredibly hot and blasts out intense radiation. This outward radiation pressure eventually pushes back against the inward pull of gravity, creating a bottleneck known as the Eddington limit, named after British astrophysicist Arthur Eddington, who figured it out in the early 1900s. For a standard supermassive black hole, this limit dictates that doubling its mass takes roughly 50 million years. Scaling up from 1,000 solar masses to 1 million requires multiple doublings, easily eating up several hundred million years. Yet, Webb is showing us black holes that blatantly ignored this speed limit, growing far too massive far too quickly. This leaves physicists with two options. Either the Eddington limit can be broken, or the initial seeds were already enormous. Both ideas are currently being heavily researched. We actually have observed super-Eddington accretion in some nearby black holes, where the geometry of the infalling gas allows radiation to vent out the sides, letting the black hole temporarily gorge itself faster than the limit allows. However, whether a black hole can sustain this chaotic feeding frenzy long enough to become a supermassive giant is highly debated. The alternative is to simply start with a massive seed. If a black hole begins its life already weighing tens or hundreds of thousands of solar masses, reaching 1 million is a breeze, and the Eddington limit is no longer a roadblock. These heavy seeds could come from two places. The first is the direct collapse of colossal early gas clouds, which skip the star-making phase entirely and implode straight into a giant black hole. The second is, of course, our primordial black holes from the Big Bang. While direct collapse is physically possible, it requires incredibly rare and specific environmental conditions. Consequently, the primordial route is rapidly becoming the favorite in recent literature. Whichever path is correct will fundamentally alter our understanding of dark matter and the behavior of the early universe. Either way, standard stellar seeds growing at the Eddington limit simply do not have the time to explain Webb's observations. Something in our standard model has to break. This brings us perfectly to the mysterious little red dots with their strange black hole star hybrid characteristics. Whatever these objects actually are, they are intimately tied to the rapid growth of these early supermassive black holes. They showed up at the exact right cosmic epoch, shone with the perfect brightness, and then vanished right as the black hole growth phase concluded. The timing is far too perfect to be a coincidence. Many experts now suspect that these little red dots are actually the glowing fingerprints of heavy seed black holes feeding at super-Eddington speeds. The incredibly thick gas clouds surrounding these feeding monsters would swallow all the X-rays, keeping them hidden from telescopes like Chandra, while glowing brightly in the infrared, which is exactly what Webb sees. This unified framework, combining primordial or direct collapse heavy seeds, super-Eddington feeding rates, and the dusty clouds of the little red dots, neatly wraps up many of the most baffling anomalies of the early universe. It is not the universally accepted consensus just yet, but it is rapidly gaining momentum. The universe Webb is revealing clearly constructed its first supermassive black holes using a playbook the standard model never anticipated. The objects are undeniably real, their masses are staggeringly huge, and the time they had to grow is impossibly short. We are absolutely forced to invoke a combination of bizarre seeds and extreme feeding habits. With every new image Webb beams back to Earth, the constraints get tighter. Our picture of the early cosmos is becoming incredibly clear and wonderfully, beautifully strange. Yet right as our picture of the early cosmos was becoming incredibly clear and wonderfully, beautifully strange, a very grounded objection emerged regarding the rotation asymmetry. What if this pattern isn't actually real? Perhaps the seemingly high number of clockwise spinning galaxies is simply an illusion created by our own movement through space. To understand this counterargument, we have to look at our cosmic address in motion. Our planet circles the Sun, which orbits the Milky Way's core. Meanwhile, our entire galaxy drifts through the local group, which travels through the Virgo supercluster, all rushing toward even grander structures. Far from sitting still, we are hurtling through the void at hundreds of kilometers per second. Naturally, traveling at such incredible speeds carries visual consequences. Photons emitted by objects directly in our path become blue-shifted, while light from things we leave behind stretches into a redshift. This movement also subtly alters perceived brightness. Galaxies we speed toward appear slightly more luminous, whereas those we speed away from look fainter. Apply this to spinning galaxies. A spiral galaxy rotating counterclockwise from our perspective has one half of its disk moving toward us, making that side brighter. Conversely, a clockwise spinning galaxy produces the exact same visual phenomenon, but with the luminous side flipped. If our trajectory favors one setup, we could detect an excess of one rotational direction simply because those galaxies shine brighter and are easier to spot. Lear Shamir openly recognized this exact scenario in his published research. He noted that if the Doppler effect is the culprit, scientists must recalibrate deep universe distance measurements. Adjusting these metrics could simultaneously solve other cosmological headaches, like the conflicting expansion rates known as the Hubble tension, and explain away mature galaxies that appear older than the universe. Think about how massive that implication truly is. If this rotational imbalance is a Doppler illusion, a single observational bias from our galaxy's movement could cause several major cosmic mysteries. Instead of discovering new physics, we would just fix a measurement error. The universe would behave normally, and our instruments would simply be miscalibrated. However, there is a major catch to this idea. For this theory to work, the Milky Way's rotation must significantly influence distant galaxy observations. Standard calculations suggest this effect is far too tiny to generate the observed asymmetry. Shamir highlights that if the imbalance is Doppler-driven, our galaxy must be spinning faster than believed. Our calibrations contain systematic flaws, or both. Blaming the Doppler effect is arguably the most mundane explanation for this mystery, yet it carries a heavy practical burden. Overhauling distance metrics would force us to rewrite every sky survey, redshift calculation, and mass estimate built on the cosmic distance ladder. Conversely, the alternative, that the universe possesses a preferred axis established at creation, is far more thrilling. That scenario demands we accept a universe born with an inherent spin, perhaps inside a parent black hole, which stamped its signature onto galaxy formation. Shamir lays out both paths and lets the evidence decide. Upcoming studies with larger datasets will reveal if this asymmetry is genuine or a statistical mirage. Both outcomes would fundamentally alter cosmology. Let's dig a bit deeper into the Doppler scenario. If it truly explains the asymmetry, our galaxy's spin exerts a much grander influence than standard models predict. Historically, most astronomers consider the Milky Way's rotation a firmly established metric. Our Sun circles the galactic core at roughly 230 kilometers per second, completing a lap every 230 million years, meaning we have finished exactly one orbit since the early dinosaurs. Scientists derived these figures by tracking local stars and gas. While not flawless, these values are tightly restricted by independent techniques. Nevertheless, Shamir's work implies we have underestimated how this local spin affects deep space vision. If his detected imbalance is a Doppler illusion, the Milky Way boosts the apparent brightness of faraway galaxies far more than conventional wisdom permits. This realization is deeply unsettling for the field. It suggests a subtle, unnoticed bias has infected decades of cosmic distance calculations. A stubborn error from our galactic movement could be woven into published data regarding the age, mass, and distance of galaxies. The ripple effects of such a mistake would be immediate and vast. Since calculating mass relies on exact distance, flawed distances mean flawed masses. Consequently, those gigantic early galaxies spotted by Webb might be smaller than claimed, easing the paradox of mature galaxies in the infant universe. Furthermore, this could impact the Hubble tension. Because local expansion measurements rely on a delicate chain of calibrations, a concealed Doppler bias could shift the local rate by the exact margin required to match the early universe's rate. Achieving such a result would be nothing short of spectacular. One hidden flaw, elegantly solving numerous riddles at once, eliminates the need for exotic dark matter, primordial black holes, or radical new physics. The most straightforward answer to our biggest mysteries might simply be a calibration blind spot. However, actually executing this fix is incredibly difficult. The bias must be highly specific, altering distance metrics just enough to cure the Hubble tension while generating the exact rotational asymmetry we observe. Crucially, it must leave the cosmic microwave background untouched and align perfectly with supernova records, galaxy clustering, and gravitational lensing without contradictions. Engineering a Doppler correction that achieves this without shattering other models is a monumental task. While some scientists believe it is possible, others dismiss the theory as a red herring that crumbles under scrutiny. As always, uncovering the ultimate truth demands vastly more data, including massive new samples of galaxy spins, expansive sky surveys, and independent evaluations of the Milky Way's true influence. In a 2025 study, Shamir concluded that astronomers must incorporate the Milky Way's rotational speed when analyzing distant galaxies. His advice is crystal clear. Regardless of which theory wins, this effect is too massive to ignore. Whether this quirk points to a cosmic anomaly or an observational flaw, it delivers a vital lesson. Earth is not the perfectly stable viewing platform we assumed. Our home galaxy moves, and that motion matters. Building on that local motion, let us evaluate modern cosmology today. Rather than finding a single flaw, Webb has revealed multiple contradictions with the standard model. While a few anomalies might connect, most likely stand alone. Mature early galaxies defy standard structure formation timelines. Supermassive black holes emerge too early for conventional seeding mechanisms. Rotation asymmetry points to a preferred cosmic axis. The stubborn Hubble tension remains, even after independent checks confirm measurement accuracy. Mysterious little red dots represent objects lacking any clear analog in older theories. Elongated early galaxies hint dark matter might not act as the standard model assumes. Finally, galaxies older than the universe itself suggest the cosmic age might be wrong. Each discovery is a fracture. Individually, we could patch them by carefully tweaking the existing framework. Together, they suggest the foundation itself is straining. What might cause all these cracks at once? Experts propose several possibilities, though none are universally accepted, and each has supporters and critics. First, the standard model might be fundamentally correct, but missing auxiliary ingredients like early dark energy, primordial black holes, or modified dark matter properties. Combined, these might patch the cracks while leaving the core framework intact. Second, a foundational assumption might be wrong. If the cosmological principle, the idea that the universe is identical in every direction, is mistaken, it naturally fits the rotation asymmetry. It might also explain the Hubble tension if local expansion rates differ from global ones. Third, gravity itself might behave differently at large scales than general relativity predicts. Modified gravity theories have a long history where most failed, but Webb has given new life to several persisting proposals. A fourth, more dramatic possibility is that the universe is not what we assumed. Embracing black hole cosmology, older universe scenarios, or alternative dark matter models would represent a substantial rewriting of the cosmic story. Most cosmologists are not yet ready for these dramatic options. The standard model has survived a long stretch of testing, so replacing it requires more than just suggestive observations. But those suggestive observations are accumulating fast. Each new Webb image, survey, and analysis adds data, and the cracks are widening, not closing. Capturing this moment perfectly, a senior cosmologist stated that cosmology is in a renaissance, not a crisis. Exactly. A crisis implies something is broken beyond repair. A renaissance implies a period of intense rebuilding where old certainties give way to new ideas and the boundaries of possibility expand. Driven by Webb, This renaissance has been underway for a few years, revealing theoretical gaps. Next comes constructing new theories to fill those gaps. Some will succeed, while most will fail. The eventual winner might be a refined standard model with additional ingredients, or it might be something far stranger. The galaxies older than the universe, the spinning patterns, the impossible black holes, and the missing red dots are all clues. The puzzle they assemble remains unsolved. The pieces are still being laid out. What we can say is that the universe is more complicated than the standard model predicted. The simplest version of the cosmic story is not quite right, and the real story has surprises that nobody anticipated. To make sense of these unexpected twists, we have to look at the very foundation of modern physics, starting with a theory that is now over a century old. Albert Einstein introduced general relativity back in 1915, meaning this foundational framework has been around for more than 110 years. Throughout the decades, it has successfully cleared every single experimental hurdle, from the gravitational redshift of light and the peculiar orbit of Mercury to the bending of starlight around the Sun. We have even verified the slowing of time within gravitational fields and detected gravitational waves rippling from smashing black holes, with every single trial confirming Einstein's math to an astonishing degree of exactness. However, this brilliant model actually forecasts its own ultimate failure. When you look at the very instant of the Big Bang or the core of a black hole, the formulas spit out singularities, locations of infinite density where the mathematics completely falls apart. Rather than viewing these mathematical crashes as defects, physicists see them as crucial markers indicating that a more profound set of rules must govern these extreme realms. This brings us to the second massive pillar of modern science, quantum mechanics, which is also over 100 years old and matches laboratory experiments with almost ridiculous precision. The catch is that we have never managed to seamlessly merge these two giants. Whenever we zoom into the microscopic scales where quantum phenomena should dictate gravitational behavior, their predictions fiercely clash. Trying to solve this puzzle of quantum gravity has occupied brilliant minds for generations, with loop quantum gravity and string theory emerging as the top contenders for a unified model. Unfortunately, neither option has yielded concrete, testable predictions so far, because they both describe reality at distances vastly smaller than our best technology can measure. While the James Webb Space Telescope isn't directly examining quantum gravity, it is peering into the infant universe, the exact environment where these quantum gravitational effects would be most critical, thereby stretching the limits of our current understanding. The cosmic structures Webb captures, such as surprisingly mature early galaxies, unexpected rotation asymmetries, and ancient supermassive black holes, are deeply tied to the initial conditions of the cosmos. If you rewind those initial conditions far enough, you inevitably hit the quantum gravity domain. Even tiny tweaks to quantum mechanics or general relativity during that primordial epoch could drastically alter these results, suggesting that Webb's data might actually be skimming the very edge of where our established physics stops working. Consequently, researchers are actively investigating altered gravity models tailored for the early cosmos, while others are examining how quantum mechanics might operate on a massive cosmic scale, with each new idea offering distinct forecasts for Webb to verify. Although the traditional pairing of general relativity and the standard cosmological model still offers the most accurate overall match despite the previously mentioned tensions, no single alternative has claimed victory just yet. Nevertheless, Webb's discoveries have essentially unlocked the door for competing ideas. Concepts like primordial black holes, ultralight dark matter, black hole cosmology, quantum cosmology, and modified gravity are no longer just mathematical daydreams. They now have a legitimate seat at the table backed by actual observational hints. Einstein's genius will almost certainly endure because its predictive strength is simply too massive to discard, though we may need to add new ingredients or modify how it applies to the grandest scales and the dawn of time. This mirrors the historical evolution of physics, where Einstein didn't erase Newton's beautifully accurate everyday mechanics, but rather expanded it to cover extreme speeds and intense gravity. In the same way, a future paradigm will likely build upon Einstein's work to better explain the ultimate boundaries of the cosmos, and Webb is currently highlighting exactly where those upgrades are required. Looking up from Earth, it is incredibly humbling to realize that the century-old rules guiding our reality are groaning under the weight of fresh data. This stress isn't a total fracture, but rather a cosmic invitation to refine our understanding, proving that while the ultimate answer remains hidden in the stars or the math, Webb has finally allowed us to see the question with perfect clarity. Building on that newfound clarity, let us play with a wild thought experiment where every bizarre theory actually holds water. Picture our reality sprouting from inside a spinning black hole within a grander mother universe. That colossal spin would stamp a directional bias onto galaxy assembly, perfectly explaining the lopsided patterns we detect. Furthermore, envision ancient black holes popping into existence during the first second following the Big Bang, acting as blueprints for early star clusters and dark matter. Here, dark matter behaves as an incredibly light, wave-like substance weaving into sleek threads instead of chunky clouds. Add in the very real Hubble tension, hinting at undiscovered physics like evolving dark energy. Should every concept prove accurate, we would throw out the standard textbook model. We would inhabit a radically distinct realm boasting a cosmic mother, possessing an inherent spin, constructed from ancient seeds instead of dying stars, and filled with invisible quantum waves rather than discrete particles. While most researchers do not currently subscribe to this exact picture, modern observations genuinely support it as a viable option. Just being able to debate it seriously represents a monumental leap forward. 2 decades back, you would have been laughed out of the room for suggesting such things. These concepts lingered on the fringes of astrophysics, championed only by a handful of rebellious thinkers, while the establishment ignored them. Thanks to the James Webb Space Telescope, the entire dialogue has transformed. Fringe theories migrated right into the spotlight, forcing the scientific consensus to embrace scenarios rejected 10 years ago. This paradigm shift reaches far past pure physics into philosophy. Discovering our reality is just one offspring in a vast family tree of parent and child universes rewrites our understanding of fundamental existence. Debates surrounding fine-tuning gain fresh perspective, especially regarding the anthropic principle. This concept, suggesting we only see a life-friendly reality because we could not exist to observe a hostile one, suddenly feels much more tangible. Similarly, if ancient black holes act as both dark matter and galactic anchors, a single entity bridges the dawn of time with the modern era. Imagine a gravitational titan born in the first second of creation, surviving 14 billion years to hold a galaxy together and frame our cosmic perspective. That paints a profoundly unique biography for our universe. Meanwhile, wave-like dark matter would intimately link the microscopic quantum realm with grand cosmic structures. Reality would not just be a swarm of tiny dots, but a layered tapestry of waves where everyday objects materialize from a quantum foundation. While physicists understand this behavior locally, witnessing it operate across the universe is unprecedented. Furthermore, a genuine universal spin implies space holds a memory. The birth of everything was not a total reset. The mother universe permanently stamped its signature onto our reality. Of course, none of these thrilling scenarios are guaranteed, and rigorous testing will undoubtedly debunk several. Over the coming decade, powerful observatories like the Roman Space Telescope, the extremely large telescope, and advanced survey tools will bring these blurry concepts into sharp focus. We will watch as flawed theories are discarded, valid ones proven, and fresh hypotheses take their place. Yet one thing is certain: reality is vastly more intricate, deeply intertwined, and wonderfully weirder than traditional models predicted. Our cosmos is not the result of a basic formula, but an elaborate narrative with unfinished chapters. Webb has acted as the ultimate magnifying glass, bringing this complexity into view and flawlessly executing its mission. It revealed the unexpected, beautifully shattered outdated assumptions and perfectly set the stage for tomorrow's breakthroughs. No matter the final truths, the mysteries we explore now are infinitely more profound than anything imagined prior to this incredible telescope taking flight. To truly appreciate this profound shift, let's pause for a moment right at the frontier of modern knowledge. According to our standard timeline, the cosmos is about 13.8 billion years old, packed with hundreds of billions of galaxies. Every single one of those galaxies harbors hundreds of billions of stars, and most anchor a supermassive black hole at their core. An unseen framework of dark matter binds this colossal architecture together, while an enigmatic push called dark energy accelerates its expansion. This established picture has passed a century of rigorous scrutiny, yet today, fractures are appearing in the foundation. We can actually name these specific fractures: the Hubble tension, mature early galaxies, mysterious little red dots, asymmetrical rotations, strangely stretched young galaxies, and galaxies appearing older than the cosmos itself. Every puzzle has spawned its own research papers and theoretical fixes. Yet they share a common catalyst, having been exposed or intensified by the James Webb Space Telescope. After lifting off in December 2021 and settling into its orbital outpost a million miles away, this observatory started beaming back pictures that completely caught scientists off guard. While built specifically to probe the dawn of time, a task it executed flawlessly, it simultaneously proved the infant cosmos looks nothing like our predictions. These discrepancies are far from minor statistical glitches or background noise. They are genuine, enduring, and multiplying anomalies. The biggest debate in modern astronomy is whether our current model can be patched to accommodate Webb's findings, or if we need to build a radically new framework from scratch. Don't expect a final verdict this year, or probably even this decade. Fresh observations are continuously pouring in, theoretical physics is actively evolving, and fierce debates are still raging. The upcoming era of cosmic discovery is currently being authored through academic journals, professional symposiums, and passionate late-night discussions among researchers. Even though these exchanges are highly complex and technical, the field is advancing at a breakneck pace. A veteran cosmologist perfectly captured this era, comparing Webb's observations to watching the cosmos in high definition for the very first time. Because the signal-to-noise ratio has skyrocketed, previously fuzzy concepts are crystal clear, and vague uncertainties transformed into hard facts. However, this sharpness exposes contradictions that lower-resolution instruments conveniently masked. Our conventional model functioned fine when measurements were less precise, but Webb's exactness exposes the weak stitches in our theories. Researchers are currently figuring out which theoretical rips can be mended with minor tweaks, and which demand a complete structural overhaul. For everyday stargazers, the main lesson is straightforward and exciting. The actual cosmos is vastly more fascinating than the textbook narrative. Our prevailing model isn't incorrect, just unfinished, and the final version will undoubtedly be weirder. We are finding galaxies rotating the wrong way, possessing impossible masses, and expanding at conflicting rates. We see tiny red dots popping in and out of cosmic time, dark matter potentially behaving as a wave, black holes predating stars, and the possibility that our universe sits inside a grander structure. Half a decade ago, these concepts belonged in sci-fi novels, but thanks to Webb, they are now focal points of rigorous scientific debate. Moving forward, our progress relies on upcoming observatories, the next 10 years of observations, and fresh theoretical breakthroughs. It hinges on uncollected data, unformulated ideas, and unforeseen surprises. If recent history is any indicator, those shocking revelations will keep coming. The cosmos is far vaster, stranger, and more honest than we ever realized. Webb revealed a reality that breaks our old maps, forcing us to redraw them. The universe has patiently guarded its secrets for billions of years, and it is finally starting to share them.